Cool. We're live.
Like now?
Yep, we're live.
Cool.
All right.
Sweet. And should I double check with it whether the audio is working, or you see that it's good?
I see it's good on my side. You want me to share my screen?
Cool. Yes, please.
All right. All right. So you
Cool.
see lesson 2?
So we're here for, yes,
Cool.
looking good. Did you open yeah, can you look at the notebook for a second before we start the video?
All right.
The one that I sent over, and just make sure that it can run.
Oh.
That was our homework from last time, that we make sure that we can run a GPU.
Oh, geez.
Do you want an intermission? I can show some stuff in the meantime while you do that. Let me take over the screen for a second.
All right. Accounts.youtube. All right.
Oh, you get it. Nice. Okay, wait. Change don't run. Remember what we need to do every time before we run a Colab notebook.
What do we do?
Oh, we want to change the runtime to GPU
Ah.
so that we don't have to wait 1.5 hours.
All right. Where is connect?
No, it's I'll let you figure it out. I don't think you have to do that, whatever you just did. That's it. Nice. It's okay.
All right. It's on a GPU now. Cool.
Oh, perfect. And it's running nice. It's installing. So you're gonna have to get that. You're gonna get that prompt again.
Yeah.
And then, but I think it's looking good. So now we know how to do that. That's good.
Yeah.
To actually get a GPU up here.
All right. Sounds good. You want to jump into the videos? Cool.
Get going.
All right. Let's make
This
this.
lesson 2, and in the last lesson we started
Sure.
training
I'm
our
gonna have to
first
read.
models.
Thanks.
We didn't really have any idea how that training was really working, but we were looking at a high level at what was going on, and we learned about what is machine learning and how does that work, and we realized that based on how machine learning worked, that there were some fundamental limitations on what it can do, and we talked about some of those limitations. And we also talked about how after you've trained a machine learning model, you end up with a program which behaves much like a normal program, something with inputs and a thing in the middle and outputs. So today we're going to finish up talking about that, and we're going to then look at how we get those models into production and what some of the issues with doing that might be. I wanted to remind you that there are two sets of notebooks available to you. One is the Fast book repo, the full actual notebooks containing all the text of the O'Reilly book. And so this lets you see everything that I'm telling you in much more detail. And then as well as that, there's the course v4 repo, which contains exactly the same notebooks, but with all the prose stripped away to help you study. So that's where you really want to be doing your experiment and your practice. And so maybe as you listen to the video, you can kind of switch back and forth between the video and reading, or do one and then the other, and then put it away and have a look at the course v4 notebooks and try to remember, like, okay, what was this section about, and run the code and see what happens and change it and so forth. So we were looking at this line of code where we looked at how we created our data by passing in information, perhaps most importantly, some way to label the data. We talked about the importance of labeling, and in this case, this particular data set, whether it's a cat.
Just fun reminder. So I think we talked over this whole code quite nicely last time, right? And changed it. Like also did a.
Yeah, we made a
stop,
dog. We made a dog one
right,
last time.
Which is lower, because if I remember correctly, the image just differentiate between cats and dogs and lowercase, uppercase. That was one takeaway, so that we just switched out the function here and down there in label function to is dog, and then we had these two different qualifiers, and we were successfully able to run it on our pad. Perfect. Cool. All right.
All right. I'm gonna play again.
Mm-hmm.
Oops.
for a dog, you can tell by whether it's an uppercase or a lowercase letter in the first position. That's just how this data set, they tell you in the README, works. And we also looked particularly at this idea of valid percent equals 0.2 and like what does that mean? It creates a validation set. And that was something I wanted to talk more about. The first thing I want to do though is point out that this particular labeling function returns something that's either true or false. And actually this data set, as we'll see later, also contains the actual breed of 37 different cat and dog breeds. So you can also grab that from the file name. In each of those two cases, we're trying to predict a category. Is it a cat or is it a dog? Or is it a German Shepherd or a Beagle or a Ragdoll cat or whatever? When you're trying to predict a category, so when the label is a category, we call that a classification model. On the other hand, you might try to predict how old is the animal, or how tall is it, or something like that, which is like a continuous number that could be like 13.2 or 26.5 or whatever. Anytime you're trying to predict a number, your label is a number, you call that regression. Okay, so those are the two main types of model, classification and regressions. This is very important jargon to know about. So a regression model attempts to predict one or more numeric quantities such as temperature or location or whatever. This is a bit confusing because sometimes people use the word regression as a shortcut to like a abbreviation for a particular kind of model called linear regression. That's super confusing because that's not what regression means. Linear regression is just a particular kind of regression. But I just wanted to warn you of that. When you start talking about regression, a lot of people will assume you're talking about linear regression, even though that's not what the word means. All right, so I wanted to talk about this valid percent 0.2 thing. So as we described, valid percent grabs, in this case, 20% of the data, if it's 0.2, and puts it aside, like in a separate bucket. And then when you train your model doesn't get to look at that data at all. That data is only used to decide, to show you how accurate your model is. So if you train for too long, and or with not enough data, and or a model with too many parameters, after a while, the accuracy of your model will actually get worse. And this is called overfitting. Right? So we use the validation set to ensure that we're not overfitting. The next line of code that we looked at is this one, where we created something called a learner. We'll be learning a lot more about that, but a learner is basically, or is, something which contains your data and your architecture. That is the mathematical function that you're optimizing. And so a learner is the thing that tries to figure out what are the parameters which best cause this function to match the labels in this data. So we're talking a lot more about that. But basically, this particular function, ResNet34, is the name of a particular architecture, which is just very good for computer vision problems. In fact, the name really is ResNet, and then 34 tells you how many layers there are. So you can use ones with bigger numbers here to get more parameters that will take longer to train, take more memory, more likely to overfit, but could also create more complex models. Right now, though, I wanted to focus on this part here, which is metrics equals error rate. This is where you list the functions that you want to be called with your data, with your validation data, and print it out after each epoch. An epoch is what we call it when you look at every single image in the data set once. And so after you've looked at every image in the data set once, we print out some information about how you're doing. And the most important thing we print out is the result of calling these metrics. So error rate is the name of a metric, and it's a function that just prints out what percent of the validation set are being incorrectly classified by your model. So a metric's a function that measures the quality of the predictions using the validation set. So error rate's 1. Another common metric is accuracy, which is just 1 minus error rate. So very important to remember from last week, we talked about loss. Arthur Samuel had this important idea in machine learning that we need some way to figure out how well our model is doing, so that when we change the parameters, we can figure out which set of parameters make that performance measurement get better or worse. That performance measurement is called the loss. The loss is not necessarily the same as your metric. The reason why is a bit subtle, and we'll be seeing it in a lot of detail once we delve into the math in the coming lessons. But basically, you need a function, you need a loss function, where if you change the parameters by just a little bit up or just a little bit down, you can see if the loss gets a little bit better or a little bit worse. And it turns out that error rate and accuracy doesn't tell you that at all, because you might change the parameters by such a small amount that none of your dog's predictions start becoming cats, and none of your cat predictions start becoming dogs, so like your predictions don't change and your error rate doesn't change. So loss and metric are closely related, but the metric is the thing that you care about. The loss is the thing which your computer is using as the measurement of performance to decide how to update your parameters. So we measure overfitting by looking at the metrics on the validation set. So Fast.ai always uses the validation set to print out your metrics. And overfitting is like the key thing that machine learning is about. It's all about how do we find a model which fits the data, not just for the data that we're training with, but for data that the training algorithm hasn't seen before. So overfitting results when our model is basically cheating. Our model can cheat by saying, oh, I've seen this exact picture before, and I remember that that's a picture of a cat. So it might not have learnt what cats look like in general. It just remembers, that images 1, 4, and 8 are cats, and 2 and 3 and 5 are dogs, and learns nothing actually about what they really look like. So that's the kind of cheating that we're trying to avoid. We don't want it to memorize our particular data set. So we split off our validation data. And most of these words you're seeing on the screen are from the book. Okay, so I just copied and pasted them. So if we split off our validation data and make sure that our model sees it during training, it's completely untainted by it, so we can't possibly cheat. Not quite true. We can cheat. The way we could cheat is we could fit a model, look at the result in the validation set, change something a little bit, fit another model, look at the validation set, change something a little bit. We could do that like 100 times until we find something where the validation set looks the best. But now we might have fit to the validation set, right? So if you want to be really rigorous about this, you should actually set aside a third bit of data called the test set that is not used for training and it's not used for your metrics. It's actually, you don't look at it until the whole project's finished. And this is what's used on competition platforms like Kaggle. On Kaggle, after the competition finishes, your performance will be measured against a data set that you have never seen. And so that's a really helpful approach. And it's actually a great idea to do that, like even if you're not doing the modeling yourself. So if you're looking at vendors and you're just trying to decide, should I go with IBM or Google or Microsoft, and they're all showing you how great their models are, what you should do is you should say, okay, you go and build your models, and I am going to hang on to 10% of my data, and I'm not going to let you see it at all. And when you're all finished, come back, and then I'll run your model on the 10% of data you've never seen. Now, pulling out your validation and test sets is a bit subtle, though. Here's an example of a simple little data set, and this comes from a fantastic blog post that Rachel wrote that we will link to about creating effective validation sets. And you can see basically you have some kind of seasonal data set here. Now, if you just say, okay, Fast.ai, I want to model that, I want to create my data loader using a valid percent of 0.2, it would do this. It would delete randomly some of the dots, right? Now, this isn't very helpful, because we can still cheat because these dots are right in the middle of other dots. And this isn't what would happen in practice. What would happen in practice is we would want to predict, this is sales by date, right? We want to predict the sales for next week, not the sales for 14 days ago, 18 days ago, and 29 days ago, right? So what you actually need to do to create an effective validation set here is not do it randomly, but instead chop off the end, right? And so this is what happens in all Kaggle competitions pretty much that involve time, for instance, is the thing that you have to predict is the next 2 weeks or so after the last data point that they give you. And this is what you should do also for your test set. So again, if you've got vendors that you're looking at, you should say to them, okay, after you're all done modeling, we're going to check your model against data that is 1 week later than you've ever seen before.
All right. I'm seeing we're dropping like 20% of frames right now. So I'm going to see if I could close a bunch of stuff really quick and then resume the video. So
I think it helps if I shouldn't make a difference whether I turn anything off, right? Because
no, I think it's I think it's me.
Yeah.
So let me just see, because I have a bunch of Safari tabs open. I'll have to find.
Oh, those browsers always eating up everything.
Seriously, I have like 8 other windows open, some of which may be using more stuff. Oh, this is from last week. I'm gonna close that.
Wait, what?
What?
You still have something open from last week?
Weird, right?
Yeah.
All right.
It's because you've been studying all the time.
It's because that's all I do.
Wow,
Okay.
I'm impressed.
Oops. All right, let's see.
And you won't be able to retrain. Because that's what happens in
I was
practice.
double checking if there's something I can close. And,
There's a question.
I nearly closed our video chat.
I've heard people describe
Very smart.
There we go. All right, let's
If you are a senior decision maker
Try it
in an
again.
organization, the most important takeaway is not. I guess I am.
You're a senior decision maker?
I guess. I never thought of myself.
Yeah,
like
yeah,
that.
you definitely are.
I guess I am.
You are. 100%. All right, I'm gonna play the video again, and then let's and then monitor
Okay.
who's actually yeah. All right. Oops.
fitting as training error being below validation error. Does this rule of thumb end up being roughly the same as yours?
Okay, so that's a great question. So I think what they mean there is training loss versus validation loss, because we don't print training error. So we do print at the end of each epoch the value of your loss function for the training set and the value of the loss function for the validation set. And if you train for long enough, so if it's training nicely, your training loss will go down and your validation loss will go down. Because by definition, loss function is defined such as a lower loss function is a better model. If you start overfitting, your training loss will keep going down, right? Because like, why wouldn't it? You know, you're getting better and better parameters. But your validation loss will start to go up because actually you started fitting to the specific data points in the training set, and so it's not going to actually get better. It's not going to get better for the validation set. It'll start to get worse. However, that does not necessarily mean that you're overfitting, or at least not overfitting in a bad way. As we'll see, it's actually possible to be at a point where the validation loss is getting worse, but the validation accuracy or error or metric is still improving. So I'm not going to describe how that would happen mathematically yet, because we need to learn more about loss functions, but we will. But for now, just realize that the important thing to look at is your metric getting worse, not your loss function getting worse. Thank you for that fantastic question. The next important thing we need to learn about is called transfer learning. So the next line of code said learn.finetune. Why does it say learn.finetune? Fine-tune is what we do when we are transfer learning. So transfer learning is using a pre-trained model for a task that is different to what it was originally trained for. So more jargon to understand our jargon. Let's look at that. What's a pre-trained model? So what happens is, remember I told you the architecture we're using is called ResNet34. So when we take that ResNet34, that's just it's just a mathematical function, okay, with lots of parameters that we're going to fit using machine learning. There's a big data set called ImageNet that contains 1.3 million pictures of 1,000 different types of thing, whether it be mushrooms or animals or aeroplanes or hammers or whatever. There's a competition, or there used to be a competition that runs every year to see who could get the best accuracy on the ImageNet competition. And the models that did really well, people would take those specific values of those parameters and they would make them available on the internet for anybody to download. So if you download that, you don't just have an architecture now, you have a trained model. You have a model that can recognize 1,000 categories of thing in images, which probably isn't very useful unless you happen to want something that recognizes those exact 1,000 categories of thing. But it turns out you can you can start with those weights in your model and then train some more epochs on your data, and you'll end up with a far, far more accurate model than you would if you didn't start with that pre-trained model. And we'll see why in just a moment, right? But this idea of transfer learning, it makes intuitive sense, right? ImageNet already has some cats and some dogs in it. It's, it can say this is a cat and this is a dog, but you want to maybe do something that recognizes lots of breeds that aren't in ImageNet. Well, for it to be able to recognize cats versus dogs versus airplanes versus hammers.
This is how the computers and the machines take over, by the way.
Right.
This is how all the machines are going to take over, through transfer learning.
Explain.
You just train, like Tesla could just train or comma AI, for example, right, could train all of their self-driving cars and then put all of that value, all that information out there, and now all the cars are self-driving. It's not like you have to teach like a dog, right? You have to teach each dog individually. You have to teach every car individually. Anyway,
I don't even think that's transfer learning.
goodbye.
Bye.
It has to understand things like, what does metal look like? What does fur look like? What it is look like? So it can say like, oh, this breed of animal, this breed of dog has pointy ears, and oh, this thing is metal, so it can't be a dog. So all these kinds of concepts get implicitly learnt by a pre-trained model. So if you start with a pre-trained model, then you don't have to learn all these features from scratch. And so transfer learning is the single most important thing for being able to use less data and less compute and get better accuracy. So that's a key focus for the Fast.ai library and a key focus for this course.
There's a question. I'm a bit confused on the differences between loss, error, and metric.
Loss, error, and metric. Sure. So error is just one kind of metric. So there's lots of different possible labels you could have. Let's say you're trying to create a model which could predict how old a cat or a dog is. So the metric you might use is, on average, how many years were you off by? So that would be a metric. On the other hand, if you're trying to predict whether this is a cat or a dog, your metric would be, what percentage of the time am I wrong? So that latter metric is called the error rate. Okay, so error is one particular metric. It's a thing that measures how well you're doing. And it's like, it should be the thing that you most care about. So you write a function or use one of Fast.ai's predefined ones, which measures how well you're doing. Loss is the thing that we talked about in lesson 1. So I'll give a quick summary, but go back to lesson 1 if you don't remember. Arthur Samuel talked about how a machine learning model needs some measure of performance, which we can look at when we adjust our parameters up or down. Does that measure of performance get better or worse? And as I mentioned earlier, some metrics possibly won't change at all if you move the parameters up and down just a little bit. So they can't be used for this purpose of adjusting the parameters to find a better measure of performance. So quite often we need to use a different function. We call this the loss function. The loss function is the measure of performance that the algorithm uses to try to make the parameters better. And it's something which should kind of track pretty closely to the metric you care about. But it's something which, as you change the parameters a bit, the loss should always change a bit. And so there's a lot of hand waving there because we need to look at some of the math of how that works. And we'll be doing that in the next couple of lessons. Thanks for the great questions. Okay, so fine-tuning is a particular transfer learning technique where the...
Oh, and you're still showing your picture and not the slides.
So fine-tuning is a transfer learning technique where the weights, this is not quite the right word, we should say the parameters, where the parameters of a pre-trained model are updated by training for additional epochs, using a different task to that used for pre-training. So pre-training, the task might have been ImageNet classification, and then our different task might be recognizing cats versus dogs. So the way, by default, Fast.ai does fine-tuning is that we use one epoch, which remember is one, looking at every image in the dataset once, one epoch to fit just those parts of the model necessary to get the particular part of the model that's specially for your dataset working, and then we use as many epochs as you ask for to fit the whole model. And so this is more for those people who might be a bit more advanced. We'll see exactly how this works later on in the lessons. So why does transfer learning work?
Can you stop this for a second?
The best way, in my opinion, to look at this is to see this paper by Zeiler and Fergus.
I could just go back to the previous slide that he had on.
Sure.
Okay. Wait, no, that's good. Just can we think that through for a second? Let me try. So fine tuning. So generally transfer learning, my understanding is we have a pre-trained model that works. Like this ImageNet is a great example that already knows how to classify stuff. And then you take this whole ImageNet and you do some more training on it. Like you take the model, I hope I'm using the right term here, or maybe architecture. What would that be?
I guess finish your thought and we could...
Okay, so yeah, so we take that model and we're already able to predict relatively well, classify images according to like, that's a plane, that's a dog. And then transfer learning means I take this model as the basis and then do some more training on top of it. Like
so
I don't start from zero, but I start with this model.
That's you take the parameters from the model that's trained, you apply it to a new I don't know if we're using the right.
Take the parameters. I think.
Like I thought that's what he said.
Architect.
Hold on.
Whoa. But
okay, so here.
Model, right? Yeah, you take the model, which is the architecture plus the parameters. Like because it needs to have like so and so many layers, and each layer has this and this parameter that applies on it. I don't think you can do anything just with the parameters, from my understanding.
I thought from what he was talking about, that where was it? That competition.
What competition? ResNet?
Yeah.
The image.
Splitting off for validation image. No. Yeah, there was something. I don't know. Anyway, there was something about the. I thought it was just like the winner of the competition was able to like grab the parameters and share the parameters for other people to use. But I guess I don't know. I guess maybe the way of doing that is just sharing this model and then using it as a base point, like a jumping point.
Right, because you need to know like how many layers to use and which types of activation, blah blah blah, all of this stuff.
Yeah,
I don't really know what it is. Yeah.
Yeah. Okay.
Okay. So all right, wait, but I think that's transfer learning, and now he's talking about fine tuning. I kind of like zoned out. I didn't completely get it. So a transfer learning technique where the weights of a pre-trained model are updated by training for additional epochs using a different task to that used for pre-training. So transfer learning, meaning we have some sort of base model that already exists. And that's the pre-trained model, yeah? So the weights of a pre-trained model are updated by training for additional epochs using a different task to that used for pre-training. Okay, so fine-tuning is transfer learning, you take the model and then you do something else with it. Isn't that just what transfer learning is? What's the fine-tuning part about it?
So the weights of a pre-trained model are updated by training for additional epochs during a different task to that used for
Use one
pre-training.
epoch to fit just those parts of the model necessary to get the new random head to work correctly with your data set. So you do one epoch of the original, the pre-trained model on your data set. That's step one,
Use
I
one
think. And you just do it in one epoch. So there you get the performance that the pre-trained model would get. And then step two, use the number of epochs requested when calling the method to fit the entire model, updating the weights of the later layers, especially the head, faster than the earlier layers. Okay, I don't get that. Updating the weights of the later layers, especially the head, faster than the earlier layer. Ah. Okay,
Do you
so
want to
because
play this section over?
Okay, I mean, yeah, sure.
Oh, because you can't really hear it, right?
Yeah, I'm reading. It's cool. It's easier for me also if I talk it out, but it's fine.
Okay. Should I speak what he's speaking, but at a delay?
No, it's rolling.
No, that's a bad. Okay, all right. I'll just play a video.
Thanks.
The algorithm uses
Thanks
to try to make the parameters better, and it's something which should kind of track pretty closely to the metric you care about, but it's something which, as you change the parameters a bit, the loss should always change a bit. And so there's a lot of hand waving there because we need to look at some of the math of how that works, and we'll be doing that in the next couple of lessons. Thanks for the great questions. Okay, so fine-tuning is a particular transfer learning technique where the...
Oh, and you're still showing your picture and not the slides.
So fine-tuning is a transfer learning technique where the weights, this is not quite the right word, we should say the parameters, where the parameters of a pre-trained model are updated by training for additional epochs, using a different task to that used for pre-training. So pre-training, the task might have been ImageNet classification, and then our different task might be recognizing cats versus dogs. So the way, by default, Fast.ai does fine-tuning is that we use one epoch, which remember is one, looking at every image in the dataset once, one epoch to fit just those parts of the model.
I'm just wondering how that's different from transfer learning. It just sounds like transfer learning. So I have the feeling I'm not getting something because
I think he just said it's a type of transfer learning, right? It's a technique.
But if you, what's the? It's a technique, yeah. But what? How can you do anything without that? Like otherwise, it's not transfer learning in my head because if you just take the pre-trained model, you're not learning anything. You're just applying the model. What are you looking for?
Transfer learning. So this is cheating.
Should I go with IBM? My DataLoader
No, it's
using
not
a valid
cheating if you go back.
0.2.
No worries. Oh god.
Transfer learning. All right.
Oh, okay.
Is that the important thing to
So,
look at
okay,
is
I see.
your metric getting worse, not your
Already
loss
read it.
function getting worse. Thank you for that fantastic one. Transfer learning. So the next line of code said learn.finetune. Why does it say learn.finetune? Fine-tune is what we do when we are transfer learning. So transfer learning is using a pre-trained model
Okay.
for a task that is different to what it was originally trained for.
Okay, so you got it?
So maybe ImageNet was designed for classifying planes, dogs, and cats, and we're using it to classify cats and dogs, which means we're doing transfer learning.
Well, he just said we use fine-tuning when we're doing transfer learning. So it just sounds like...
what Fast.ai does. All right, whatever. I'm satisfied.
I'm over it.
I don't know if you are, but I am. I'm okay.
You're satisfied, and I'm over it. So moving on.
All right, good.
Especially for your data set working, and then we use as many epochs as you ask for to fit the whole model. And so this is more for those people who might be a bit more advanced. We'll see exactly how this works later on in the lessons. So why does transfer learning work, and why does it work so well? The best way, in my opinion, to look at this is to see this paper by Zeiler and Fergus, who were actually 2012 ImageNet winners. And interestingly, their key insights came from their ability to visualize what's going on inside a model. And so visualization very often turns out to be super important to getting great results. What they were able to do was they looked, remember I told you like a ResNet 34 has 34 layers? They looked at something called AlexNet, which was the previous winner of the competition, which only had 7 layers. At the time, that was considered huge. And so they took the 7-layer model and they said, what does the first layer of parameters look like? And they figured out how to draw a picture of them, right? And so the first layer had lots and lots of features, but here are 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. And here's what 9 of those features look like. One of them was something that could recognize diagonal lines from top left to bottom right. One of them could find diagonal lines from bottom left to top right. One of them could find gradients that went from the top of orange to the bottom of blue. Some of them were able, one of them was specifically for finding things that were green, and so forth, right? So for each of these 9, they're called filters or features. So then something really interesting they did was they looked at for each one of these filters, each one of these features, and we'll learn kind of mathematically about what these actually mean in the coming lessons. But for now, let's just recognize them as saying, oh, there's something that looks at diagonal lines and something that looks at gradients. And they found in the actual images in ImageNet specific examples of parts of photos that match that filter. So for this top left filter, here are 9 actual patches of real photos that match that filter. And as you can see, they're all diagonal lines. And so here's for the green one, here's parts of actual photos that match the green one. So layer 1 is super simple. And one of the interesting things to note here is that something that can recognize gradients and patches of color and lines is likely to be useful for lots of other tasks as well, not just ImageNet. So you can kind of see how something that can do this might also be good at many other computer vision tasks as well. This is layer 2. Layer 2 takes the features of layer 1 and combines them. So it can not just find edges, but can find corners, or repeating curving patterns, or semicircles, or full circles. And so you can see, for example, here's it's kind of hard to exactly visualize these layers after layer 1. You kind of have to show examples of what the filters look like. But here you can see examples of parts of photos that this layer 2 circular filter has activated on. And as you can see, it's found things with circles. So interestingly, this one, which is this kind of blotchy gradient, seems to be very good at finding sunsets. And this repeating vertical pattern is very good at finding like curtains and wheat fields and stuff. So the further we get, layer 3 then gets to combine all the kinds of features in layer 2. And remember, we're only seeing here 12 of the features.
Can you pause for a second again?
I don't remember exactly in AlexNet, but there's lots. But by the time we get to layer 3,
this is also interesting because I don't know if you know that, but I think vision itself, like vision for humans, or I guess mammals probably, supposedly works in a similar way that there's like this layers of perception that you activate, like that. One of the first things that we supposedly notice are edges of things. Mm-hmm. So this is a line, this is a shape over there, and then a lot of like processing power gets kind of like redirected, or I don't know, like you take it off the eyes to actually have the responsibility to perceive all of the data, but you just grab the edges, and then a lot of stuff gets auto-completed in the brain, especially when you're in familiar environments. Then you actually don't perceive things very often, but you just grab the rough, like the rough shapes of things, and then the brain does the rest in an auto-completion. There's something cool about this similar vision layers happening to how these layers happen in the machine learning algorithms. I don't know, I read that at some point.
Nice. Very cool. All right, are we good to
yeah, sure.
What are you complaining about? Sorry, Regs is also, he's kind of complaining. Do you want me to take my headphones off? You want to learn machine learning too? No? He's gonna be the smartest dog. He's
listening all the time.
Yeah.
Combining features from layer 2, it already has something which is finding text. So this is a feature which can find bits of image that contain text. It's already got something which can find repeating geometric patterns. And you see, this is not just like a matching specific pixel patterns. This is like a semantic concept. It can find repeating circles or repeating squares or repeating hexagons, right? So it's really like computing. It's not just matching a template. And remember, we know that neural networks can solve any possible computable function, so it can certainly do that. So layer 4 gets to combine all the filters from layer 3 anyway at once. And so by layer 4, we have something that can find dog faces, for instance. So you can kind of see how each layer we get like multiplicatively more sophisticated features. And so that's why these deep neural networks can be so incredibly powerful. It's also why transfer learning can work so well, because like if we wanted something that can find books, and I don't think there's a book category in ImageNet, well, it's actually already got something that can find text as an earlier filter, which I guess it must be using to find, maybe there's a category for library or something, or a bookshelf. So when you use transfer learning, you can take advantage of all of these pre-learnt features to find things that are just combinations of these existing features. And that's why transfer learning can be done so much more quickly and so much less data than traditional approaches. One important thing to realize then is that these techniques for computer vision are not just good at recognizing photos. There's all kinds of things you can turn into pictures. For example, these are sounds that have been turned into pictures by representing their frequencies over time. And it turns out that if you convert a sound into these kinds of pictures, you can get basically state-of-the-art results at sound detection just by using the exact same ResNet learner that we've already seen.
I wanted to highlight that it's 9:45, so if you want to take a break soon.
A really cool example from, I think this was our very first year of running Fast.ai. One of our students created pictures. They worked at Splunk in anti-fraud, and they created pictures of users moving their mouse. And if I remember correctly, as they moved their mouse, he basically drew a picture of where the mouse moved. And the color depended on how fast they moved, and these circular blobs is where they clicked the left or the right mouse button. And at Splunk, they then, what he did actually for the course, as a project for the course, is he tried to see whether he could use these pictures with exactly the same approach we saw in lesson 1 to create an anti-fraud model. And it worked so well that Splunk ended up patenting a new product based on this technique. And you can actually check it out. There's a blog post about it on the internet where they describe this breakthrough anti-fraud approach, which literally came from one of our really amazing and brilliant and creative students after lesson 1 of the course. Another cool example of this is looking at different viruses and again turning them into pictures. And you can kind of see how they've got here, this is from a paper, check out the book for the citation. They've got 3 examples of a particular virus called vb.at and another example of a particular virus called Fakerean. And you can see in each case, the pictures all look kind of...
Pause.
Yep.
What kind of virus is the computer viruses, or is this human viruses, genome sequencing? Or
I don't know.
v2lob.p?
vb.at. Is that...
v2lob.p. Okay, it's computer viruses. Looks like it, I think.
Oh, maybe this is taking up all of my bandwidth.
Huh.
Let me just allow it. All right, Regs, why are you complaining?
Still valid, or was it too long?
No, I just did it, yeah. This, okay.
Okay, so computer viruses.
These are computer viruses, okay.
Yeah, because I was wondering whether it's genomes. Could have been some sort of visual representation of genome sequences or something.
Mm-hmm.
Okay.
That's why, again, they can get state-of-the-art results in virus detection by turning the kind of program signatures into pictures and putting it through image recognition. So in the book, you'll find a list of all of the terms, all of the most important terms we've seen so far and what they mean. I'm not going to read through them, but I want you to, please, because these are the terms that we're going to be using from now on, and you've got to know what they mean. Because if you don't, you're going to be really confused, because I'll be talking about labels and architectures and models and parameters, and they have very specific exact meanings, and I'll be using those exact meanings. So please review this. So to remind you, this is where we got to. We ended up with Arthur Samuel's overall approach.
I can hear your mic
replaced his terms with our terms.
around.
So we have an architecture which contains parameters as inputs, and parameters and the data as inputs. So that the architecture plus the parameters of the model. With the inputs they use to calculate predictions, they are compared to the labels with a loss function, and that loss function is used to update the parameters many, many times to make them better and better until the loss gets nice and super low. So this is the end of chapter 1 of the book. It's really important to look at the questionnaire, because the questionnaire is the thing where you can check whether you have taken away from this book, of this chapter, the stuff that we hope you have. So go through it, and anything that you're not sure about, the answer is in the text. So just go back to earlier in the book and you will in the chapter, and you will find the answers. There's also a further research section after each questionnaire. For the first couple of chapters, they're actually pretty simple. Hopefully they're pretty fun and interesting. They're things where to answer the question, it's not enough to just look in the chapter. You actually have to go and do your own thinking and experimenting and Googling and so forth. In later chapters, some of these further research things are pretty significant projects that might take a few days or even weeks. And so, yeah, check them out, because hopefully they'll be a great way to expand your understanding of the material. So something that Sylvain points out in the book is that if you really want to make the most of this, then after each chapter, please take the time to experiment with your own project and with the notebooks we provide, and then see if you can redo the notebooks on a new data set. Perhaps for chapter 1 that might be a bit hard because we haven't really shown how to change things, but for chapter 2, which we're going to start next, you'll absolutely be able to do that. Okay, so let's take a 5-minute break, and we'll come back at 9:55 San Francisco time.
Break.
Okay, so welcome back, everybody, and I think we've got a couple of questions to start with.
That was a
Please
fast
take it
break.
away.
Sure.
It's
Our filters
over.
ended. By that,
That was a very fast break. That was not 5 minutes. I was excited. You get up, stretch.
I'm gonna do that right now.
You want to take a little break?
Just stretching.
Just stretching. All right. Yeah, I'm putting my mic on mute because Regs is trying to eat my hand, and he's banging into it. So, also these cables. I don't know how to fix this. But anyway, all right. Shall we?
Stretched. I'm stretched.
You're
There you go.
stretched. All right. Cool.
I mean, if filters are pre-trained, might they become less good at detecting features of previous images when fine-tuned?
Oh, that is a great question. So assuming I understand the question correctly, if you start with, say, an ImageNet model, and then you fine-tune it on dogs versus cats for a few epochs, and you get something that's very good at recognizing dogs versus cats, it's going to be much less good as an ImageNet model after that. So it's not going to be very good at recognizing aeroplanes or hammers or whatever. This is called catastrophic forgetting in the literature. The idea that as you see more images about different things to what you saw earlier, that you start to forget what the things you saw earlier are. So if you want to fine-tune something which is good at a new task but also continues to be good at the previous task, you need to keep putting in examples of the previous task as well.
And what are the differences between parameters and hyperparameters? If I am feeding an image of a dog as an input and then changing the hyperparameters of batch size in the model, what would be an example of a parameter?
So the parameters are the things that are described in lesson 1 that Arthur Samuel described as being the things which change what the model does, what the architecture does. So we start with this infinitely flexible function, a thing called a neural network that can do anything at all. And the way you get it to do one thing versus another thing is by changing its parameters. They are the numbers that you pass into that function. So there's 2 types of numbers you pass into the function. There's the numbers that represent your input, like the pixels of your dog, and there's the numbers that represent the learnt parameters. So in the example of something that's not a neural net, but like a checkers playing program, like Arthur Samuel might have used back in the early 60s and late 50s, those parameters may have been things like if there is a opportunity to take a piece versus an opportunity to get to the end of a board, how much more value should I consider one versus the other? It's twice as important, or it's 3 times as important. That 2 versus 3, that would be an example of a parameter. In a neural network, parameters are a much more abstract concept, and so a detailed understanding of what they are will come in the next lesson or 2. But it's the same basic idea. They're the numbers which change what the model does to be something that recognizes malignant tumors versus cats versus dogs versus colorizes black and white pictures. Whereas the hyperparameter is the choices about what numbers do you pass to the function when you the actual fitting function to decide how that fitting process happens.
There's a question. I'm curious about the pacing of this course. I'm concerned that all the material may not be covered.
Depends what you mean by all the material. We certainly won't cover everything in the world. So yeah, we'll cover what we can. We'll cover what we can in 7 lessons. We're certainly not covering the whole book, if that's what you're wondering. The whole book will be covered in either 2 or 3 courses. In the past, it's generally been 2 courses to cover about the amount of stuff in the book. But we'll see how it goes because the book's pretty big, 500 pages. So
When you say 2 courses, you mean 14 lessons?
14, yeah, so it'll be like 14 or 21 lessons to get through the whole book. Although having said that, by the end of the first lesson, hopefully there'll be kind of like enough momentum and understanding that reading the book independently will be more useful, and you'll have also kind of gained a community of folks on the forums that you can hang out with and ask questions of and so forth. So in the second part of the course, we're going to be talking about putting stuff in production. So to do that, we need to understand what are the capabilities and limitations of deep learning? What are the kinds of projects that even make sense to try to put in production? And one of the key things I should mention in the book and in this course is that the first 2 or 3 lessons and chapters, there's a lot of stuff which is designed not just for coders, but for everybody. There's lots of information about what are the practical things you need to know to make deep learning work. And so one of the things you need to know is well, what's deep learning actually good at the moment? So I'll summarize what the book says about this, but there are the kind of 4 key areas that we have as applications in Fast.ai: computer vision, text, tabular, and what I've called here Regs. This stands for recommendation systems, and specifically a technique called collaborative filtering, which we briefly saw last week.
Sorry, another question. Are there any pre-trained weights available other than the ones from ImageNet that we can use? If yes, when should we use others and when ImageNet?
Oh, that's a really great question. So yes, there are a lot of pre-trained models, and one way to find them.
And also, you're currently just showing.
Yeah, I'm just switching.
Okay, great.
And one great way to find them is you can look up Model Zoo, which is a common name for like places that have lots of different models. And so here's lots of model zoos. Or you can look for pre-trained models. And so, yeah, there's quite a few. Unfortunately, not as wide a variety as I would like. Most are still on ImageNet or similar kinds of general photos. For example, medical imaging, there's hardly any. There's a lot of opportunities for people to create domain-specific pre-trained models. It's still an area that's really underdone because not enough people are working on transfer learning.
Interesting. So, wonderful. He found a ball, and now he's just running around the room. Anyway, so is this? I was thinking, should we look at some point maybe some model zoos and see like where we see, maybe we can like train something, as like a project.
Like make one of these pre-trained models or what? Is
Yeah,
that what
like
you're saying?
yeah, like make a model. I don't know what for yet, but I think that would be kind of cool. Seeing that somebody also like patented a full-blown application after taking this course. It'd be kind of cool if we did something kind of significant.
Yeah, I'm just thinking about like what would be area of expertise things that we could do something about.
I don't know.
Image.
Something to think about.
Yeah, something to think about.
Something to think about. All right. Pressing play.
Wait, actually,
Yeah.
that's a nice still image. Let's look at it for a second. Vision, detection, classification, text, classification, conversation, tabular, high cardinality, GPU rapids. I don't know what that means.
I don't know.
Wait, cardinality, what does it mean? Do you know?
I do not. Do you want to?
I think it's related to. Yeah, can you Google it? I think it's related to database structures.
I was gonna say, do you want to look at it? I'm gonna put him in a different room. And do you want to share your screen?
Can I just take over like that?
Here, I could stop sharing. Okay. And then, there you go. I'll be back.
Cool. Let's see. We were looking at cardinality. What is cardinality of category, categorical? Cardinality. Maybe I'm mixing these two up, and they shouldn't be mixed up, but I'm just checking. It takes a while to, it's super confusing. Okay, it means two things. Come on, where's the definition? Data cardinality, that's probably what this is talking about. How many distinct values are in a column? That makes sense. Cardinality. Reduce cardinality of categorical variables. Okay, so when you have a lot of unique values, you want to reduce the amount of unique values that exist. High cardinality string categorical variables. Yeah, makes sense. Okay, it would mean it's not in a database setting. Right, what can I do in the meantime? Look at this, reconnect. Just doing a little bit of preview until Nick gets back, because he's got the stream going. In this chapter, we're going to use a computer vision example to look at the end-to-end process of creating deep learning application. Be a classifier. Does in, such as does in where? From similar in key respects, for example, expected to get excellent results with little code quickly. So what could we classify? We could classify different cat breeds. That's kind of boring. I wonder how, like, leaves, plant classifiers, how well these.
All right, I'm back.
I
Hello.
was just looking a little bit ahead of the project that we're going to work on.
Nice.
I'm thinking about, so it's going to be a classifier, essentially an image classifier. I was wondering what we could classify on. Anyways, but all good. You can take back over.
right.
Over.
Share screen, desktop 2. Oops, not that.
Okay, so as I was mentioning, we've kind of got these 4 applications that we've talked about a bit, and deep learning is pretty good at all of those. Tabular data, like spreadsheets and database tables, is an area where deep learning is not always the best choice. But it's
yeah,
good
cardinality. I looked it up. Sorry, you weren't here.
That means variables.
So cardinality just means that there's a lot of different.
Product ID.
Is he talking? Are you talking?
Deep learning is really great for those in particular.
Is it playing? Oh yeah, okay.
Yeah, go for it. Cardinality. Yeah, I noticed that, like, so because you can't see, can't see my video, so I was like, your video on Zoom was underneath my video from OBS, so I couldn't see you, but I could see you on the Zoom call, but I couldn't see you on the stream. What a mess. We need to figure this out.
Right. But can you switch back on the closed captions?
Yes.
Because I don't know where it's playing. But so cardinality, if you want to know, it's just the amount of unique data points, essentially. So if you have like a table, like if you have a column, I guess how many unique, the amount of unique data points in there, I guess. Maybe the amount of unique columns or something.
Okay.
Does that make sense?
Sort of.
So cardinality is something about how many unique data points you have. I think that's what I distilled from the little that I read.
All right, cool. Yeah, we I think we may have picked probably the worst time to stream because Johnny is also, he's like, he just got back from Acadia from Maine, and he was there for like a week, and now he's got to catch up on all these projects. So Johnny's my brother, and he's a woodworker, so he's like in the backyard now, like ripping on the table saw. So I'm like going back and forth trying to like mute the mic and move my face and like all. Oh man. Anyway, a lot of multitasking going on. All right.
I'm very single tasked. I'm just focused on reading things that I can't hear.
You can't see me. You can't hear the video. You're just reading the screen. This is scrappy at best.
Different challenges.
Yes.
It's all valid.
All right, I'm gonna play the video again.
The text, it's pretty great at things like classification and translation. It's actually terrible for conversation. And so that's been something that's been a huge disappointment for a lot of companies. They try to create these like conversation bots. But actually deep learning isn't good at providing accurate information. It's good at providing things that sound accurate and sound compelling, but we don't really have great ways yet of actually making sure it's correct. One big issue for recommendation systems, collaborative filtering, is that deep learning is focused on making predictions, which don't necessarily actually mean creating useful recommendations. We'll see what that means in a moment. Deep learning is also good at multimodal. That means things where you've got multiple different types of data. So you might have some tabular data, including a text column and an image, and some collaborative filtering data. And combining that all together is something that deep learning is really good at. So for example, putting captions on photos is something which deep learning is pretty good at, although again, it's not very good at being accurate. So it might say this is a picture of 2 birds, when it's actually a picture of 3 birds. And then this other category, there's lots and lots of things that you can do with deep learning by being creative about the use of these kinds of other application-based approaches. For example, an approach that we developed for natural language processing called ULMFit that we'll be learning in the course. It turns out that it's also fantastic at doing protein analysis. If you think of the different proteins as being different words, and they're in a sequence which has some kind of state and meaning, it turns out that ULMFit works really well for protein analysis. So often it's about kind of being creative. So to decide, like, for the product that you're trying to build, is deep learning going to work well for it? In the end, you kind of just have to try it and see. But if you do a search, hopefully you can find examples of other people that have tried something similar. Even if you can't, it doesn't mean it's not going to work. So for example, I mentioned the collaborative filtering issue where a recommendation and a prediction are not necessarily the same thing. You can see this on Amazon, for example, quite often. So I bought a Terry Pratchett book, and then Amazon tried for months to get me to buy more Terry Pratchett books. Now that must be because their predictive model said that people who bought one particular Terry Pratchett book are likely to also buy other Terry Pratchett books. But from the point of view of, like, well, is this going to change my buying behavior? Probably not, right? Like, if I liked that book, I already know I like that author, and I already know that, like, they probably wrote other things, so I'll go and buy it anyway. So this would be an example of, like, Amazon probably not being very smart here. They're actually showing me collaborative filtering predictions rather than actually figuring out how to optimize a recommendation. So an optimized recommendation would be something more like your local human bookseller might do, where they might say, oh, you like Terry Pratchett? Well, let me tell you about other kind of comedy, fantasy, sci-fi writers on the similar vein who you might not have heard about before. So the difference between recommendations and predictions is super important. So I wanted to talk about a really important issue around interpreting models. And for a case study for this, I thought let's pick something that's actually super important right now, which is a model in this paper. One of the things we're going to try and do in this course is learn how to read papers. So here's a paper which I would love for everybody to read, called High Temperature and High Humidity Reduce the Transmission of COVID-19. Now this is a very important issue because if the claim of this paper is true, then that would mean that this is going to be a seasonal disease. And if this is a seasonal disease, then it's going to have massive policy implications. So let's try and find out how this was modeled and understand how to interpret this model.
I think that was filmed in like early of the year,
picture from the
February or March.
Yeah, I remember when this hit the news, and this was like they're trying to figure out if this was true or not.
Seasonality, yeah. I guess February, March,
here.
something, but
something like
it's
that.
interesting.
Yeah.
This is actually an interesting. I was going to talk about p-values.
Is they've taken 100 cities in China, and they've plotted the temperature on one axis in Celsius and R on the other axis, where R is a measure of transmissibility. It says for each person that has this disease, how many people on average will they infect. So if R is under 1, then the disease will not spread. If R is higher than like 2, it's going to spread incredibly quickly. And basically R is going to, any high R is going to create an exponential transmission impact. And you can see in this case, they have plotted a best fit line through here. And then they've made a claim that there's some particular relationship in terms of a formula, that R is 1.99 minus 0.023 times temperature. So a very obvious concern I would have looking at this picture is that this might just be random. Maybe there's no relationship at all, but just if you picked 100 cities at random, perhaps they would sometimes show this level of relationship. So one simple way to kind of see that would be to actually do it in a spreadsheet. So here's a spreadsheet where what I did was I kind of eyeballed this data and I guessed about what is the mean degree centigrade. I think it's about 5. And what's about the standard deviation of centigrade? I think it's probably about 5 as well. And then I did the same thing for R. I think the mean R looks like it's about 1.9 to me. And it looks like the standard deviation of R is probably about 0.5. So what I then did was I just jumped over here and I created a random normal value. So a random value from a normal distribution, so a bell curve, with that particular mean and standard deviation of temperature, and that particular mean and standard deviation of R. And so this would be an example of a city that might be in this data set of 100 cities, something with 9 degrees Celsius and an R of 1.1. So that would be 9 degrees Celsius and an R of 1.1. So something about here. And so then I just copied that formula down 100 times. So here are 100 cities that could be in China, right? Where this is assuming that there is no relationship between temperature and R, right? They're just random numbers. And so each time I recalculate that, so if I hit Control equals, it will just recalculate it, right? I get different numbers, okay, because they're random. And so you can see at the top here, I've then got the average of all of the temperatures and the average of all of the R's, and the average of all the temperatures varies, and the average of all of the R's varies as well. So then what I did was I copied those random numbers over here. Let's actually do it. So I'll go copy these 100 random numbers and paste them here, 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 here. And so now I've got 1, 2, 3, 4, 5, 6. I've got 6 kind of groups of 100 cities, right? And so let's stop those from randomly changing anymore by just fixing them in stone there. Okay, so now that I've pasted them in, I've got 6 examples of what 100 cities might look like if there was no relationship at all between temperature and R. And I've got their mean temperature and R in each of those 6 examples. And what I've done is, you can see here, at least for the first one, is I've plotted it, right? And you can see in this case, there's actually a slight positive slope. And I've actually calculated the slope for each just by using the slope function in Microsoft Excel. And you can see that actually, in this particular case, it's just random. 5 times it's been negative, and it's even more negative than their 0.023. And so you can, like, it's kind of matching our intuition here, which is that the slope of the line that we have here is something that absolutely can often happen totally by chance. It doesn't seem to be indicating any kind of real relationship at all. If we wanted that slope to be like more confident, we would need to look at more cities. So like here I've got 3,000 randomly generated numbers. And you can see here, the slope is 0.00002, right? It's almost exactly 0, which is what we'd expect, right? When there's actually no relationship between C and R, in this case there isn't, they're all random. Then if we look at lots and lots of randomly generated cities, then we can say, oh yeah, there's no slope. But when you only look at 100, as we did here, you're going to see relationships totally coincidentally very, very often, right? So that's something that we need to be able to measure. And so one way to measure that is we use something called a p-value. So a p-value, here's how a p-value works. We start out with something called a null hypothesis. And the null hypothesis is basically what's our starting point assumption. So our starting point assumption might be, oh, there's no relationship between temperature and R. And then we gather some data.
And have you explained what R is?
I have, yes.
Okay.
R is the transmissibility of the virus. So then we gather data of independent variables. In this case, the independent variable is the thing that we think might cause a dependent variable. So here the independent variable would be temperature, the dependent variable would be R. So here we've gathered data. There's the data that was gathered in this example. And then we say, what percentage of the time would we see this amount of relationship, which is a slope of 0.023, by chance? And as we've seen, one way to do that is by what we call a simulation, which is by generating random number, 100 set pairs of random numbers a bunch of times and seeing how often you see this relationship. We don't actually have to do it that though. There's actually a simple equation we can use to jump straight to this number, which is what percent of the time would we see that relationship by chance. This is basically what that looks like. We have the most likely observation, which in this case would be if there is no relationship between temperature and R, then the most likely slope would be 0. And sometimes you get positive slopes by chance, and sometimes you get pretty small slopes, and sometimes you get large negative slopes by chance. And so the larger the number, the less likely it is to happen, whether it be on the positive side or the negative side. And so in our case, our question was, how often are we going to get less than negative 0.023? So it would actually be somewhere down here. I actually copied this from Wikipedia where they were looking for positive numbers, and so they've colored in this area above a number. So this is the p-value. And so you can, we don't care about the math, but there's a simple little equation you can use to directly figure out this number, the p-value, from the data. So this is kind of how nearly all kind of medical research results tend to be shown, and folks really focus on this idea of p-values. And indeed, in this particular study, as we'll see in a moment, they reported p-values. So probably a lot of you have seen p-values in your previous lives. They come up in a lot of different domains. Here's the thing. They are terrible. You almost always shouldn't be using them. Don't just trust me. Trust the American Statistical Association. They point out 6 things about p-values. And those include p-values do not measure the probability that the hypothesis is true, or the probability that the data were produced by random choice alone. Now, we know this because we just saw that if we use more data, right? So if we sample 3,000 random cities rather than 100, we get a much smaller value, right? So p-values don't just tell you about how big a relationship is, but they actually tell you about a combination of that and how much data did you collect, right? So they don't measure the probability that the hypothesis is true. So therefore, conclusions and policy decisions should not be based on whether a p-value passes some threshold. P-value does not measure the importance of a result, right? Because again, it could just tell you that you collected lots of data, which doesn't tell you that the results actually have any practical import. And so by itself, it does not provide a good measure of evidence. So Frank Harrell, who is somebody who I read his book, and it's a really important part of my learning. He's a professor of biostatistics, has a number of great articles about this. He says, null hypothesis testing and p-values have done significant harm to science. And he wrote another piece called Null Hypothesis Significance Testing Never Worked. I've shown you what p-values are so that you know why they don't work, not so that you can use them. Right? But they're a super important part of machine learning because they come up all the time in making, when people saying this is how we decide whether your drug worked or whether there is an epidemiological relationship or whatever. And indeed, p-values appear in this paper. So in the paper, they show the results of a multiple linear regression, and they put 3 stars next to any relationship which has a p-value of 0.01 or less. So there is something useful to say about a small p-value, like 0.01 or less, which is that the thing that we're looking at probably did not happen by chance. Right? The biggest statistical error people make all the time is that they see that a p-value is not less than 0.05, and then they make the erroneous conclusion that no relationship exists. Right? Which doesn't make any sense, because like, let's say you only had like 3 data points, then you almost certainly won't have enough data to have a p-value of less than 0.05 for any hypothesis. So like the way to check is to go back and say, what if I picked the exact opposite null hypothesis? What if my null hypothesis was there is a relationship between temperature and R? Then do I have enough data to reject that null hypothesis? Right? And if the answer is no, then you just don't have enough data to make any conclusions at all. Right? So in this case, they do have enough data to be confident that there is a relationship between temperature and R. Now that's weird, because we just looked at the graph and we did a little bit of a back of the envelope in Excel, and we thought this could well be random. So here's where the issue is. The graph shows what we call a univariate relationship. A univariate relationship shows the relationship between one independent variable and one dependent variable. And that's what you can normally show on a graph. But in this case, they did a multivariate model in which they looked at temperature and humidity and GDP per capita and population density. And when you put all of those things into the model, then you end up with statistically significant results for temperature and humidity. Why does that happen? Well, the reason that happens is because all these variation in the blue dots is not random. There's a reason they're different, right? And the reasons include denser cities are going to have higher transmission, for instance, and probably more humid will have less transmission. So when you do a multivariate model, it actually allows you to be more confident of your results, right? But the p-value, as noted by the American Statistical Association, does not tell us whether this is of practical importance. The thing that tells us that this is of practical importance is the actual slope that's found. And so in this case, the equation they come up with is that R equals 3.968 minus 0.038 by temperature minus 0.024 by relative humidity. This is this equation. Is this practically important? Well, we can again do a little back of the envelope here by just putting that into Excel. Let's say there was one place that had a temperature of 10 centigrade and a humidity of 40. Then if this equation is correct, R would be about 2.7. Somewhere with a temperature of 35 centigrade and a humidity of 80, R would be about 0.8. So is this practically important? Oh my God, yes, right? 2 different cities with different climates can be, if they're the same in every other way, and this model is correct, then one city would have no spread of disease because R is less than 1. One would have massive exponential explosion. So we can see from this model that if the modeling is correct, then this is a highly practically significant result. So this is how you determine practical significance of your models. It's not with p-values, but with looking at kind of actual outcomes. So how do you think about the practical importance of a model, and how do you turn a predictive model into something useful in production? So I spent many, many years thinking about this, and I actually created with some other great folks, I actually created a paper about it, designing great data products. This is largely based on 10 years of work I did at a company I founded called Optimal Decisions Group. And Optimal Decisions Group was focused on the question of helping insurance companies figure out what prices to set. Insurance companies, up until that point, had focused on predictive modeling. Actuaries, in particular, spent their time trying to figure out how likely is it that you're going to crash your car, and if you do, how much damage might you have, and then based on that, try to figure out what price they should set for your policy. So for this company, what we did was we decided to use a different approach, which I ended up calling the drivetrain approach, which is described here, to set insurance prices and indeed to do all kinds of other things. And so for the insurance example, the objective would be for an insurance company would be, how do I maximize my, let's say, 5-year profit? And then what inputs can we control? Can we control, which I call levers? So in this case, it would be what price can I set? And then data is data which can tell you, as you change your levers, how does that change your objective? So if I start increasing my price to people who are likely to crash their car, then we'll get less of them, which means we'll have less costs, but at the same time, we'll also have less revenue coming in, for example. So to link up the kind of the levers to the objective via the data we collect, we build models that describe how the levers influence the objective. And this is all like, it seems pretty obvious when you say it like this, but when we started work with Optimal Decisions in 1999, nobody was doing this in insurance. Everybody in insurance was simply doing a predictive model to guess how likely people were to crash their car. And then pricing was set by like adding 20% or whatever. It was just done in a very kind of naive way. So what I did is I over many years took this basic process and tried to help lots of companies figure out how to use it to turn predictive models into actions. So the starting point in like actually getting value in a predictive model is thinking about what is it you're trying to do, and what are the sources of value in that thing you're trying to do. The levers, what are the things you can change? Like what's the point of a predictive model if you can't do anything about it, right? Figuring out ways to find what data you have, which one's suitable, what's available, then think about what approaches to analytics you can then take, and then super important, like, well, can you actually implement those changes? And super important, how do you actually change things as the environment changes? And interestingly, a lot of these things are areas where there's not very much academic research. There's a little bit, and some of the papers that have been particularly around maintenance of like how do you decide when your machine learning model is kind of still okay, how do you update it over time, have had like many citations, but they don't pop up very often because a lot of folks are so focused on the math, and then there's the whole question of like what constraints are in place across this whole thing. So what you'll find in the book is there is a whole appendix which actually goes through every one of these 6 things and has a whole list of examples. So this is an example of how to like think about value, and lots of questions that companies and organizations can use to try and think about all of these different pieces of the actual puzzle of getting stuff into production and actually into an effective product.
We have a question.
Sure, just a moment. So
Sure.
as I say, so do check out this appendix because it actually originally appeared as a blog post, and I think except for my COVID-19 post that I did with Rachel, it's actually the most popular blog post I've ever written. It's had hundreds of thousands of views, and it kind of represents like 20 years of hard-won insights about like how you actually get value from machine learning in practice and what you actually have to ask. So please check it out because hopefully you'll find it helpful. So when we think about this for the question of how should people think about the relationship between seasonality and transmissibility of COVID-19, you kind of need to dig really deeply into the questions about like, well, not just what are those numbers in the data, but what does it really look like, right? So one of the things in the paper that they show is actual maps, right, of temperature and humidity and R, right? And you can see, like, not surprisingly, that humidity and temperature in China are what we would call autocorrelated, which is to say that places that are close to each other, in this case geographically, have similar temperatures and similar humidities. And so like this actually puts into the question the p-values that they have, right? Because you can't really think of these as 100 totally separate cities, because the ones that are close to each other probably have very close behavior. So maybe you should think of them as like a small number of sets of cities, of kind of larger geographies. So these are the kinds of things that when you look actually into a model, you need to like think about what are the limitations. But then to decide like, well, what does that mean? What do I do about that? You need to think of it from this kind of utility point of view, this kind of end-to-end, what are the actions I can take, what are the results point of view, not just null hypothesis testing. So in this case, for example, there are basically 4 possible key ways this could end up. It could end up that there really is a relationship between temperature and R, or so that's what the right-hand side is, or there is no real relationship between temperature and R. And we might act on the assumption that there is a relationship, or we might act on the assumption that there isn't a relationship. And so you kind of want to look at each of these 4 possibilities and say like, well, what would be the economic and societal consequences? And, there's going to be a huge difference in lives lost and, economies crashing and whatever else, for each of these 4. The paper actually, has shown, if their model is correct, what's the likely R value in March for like every city in the world, and the likely R value in July for every city in the world. And so, for example, if you look at kind of New England and New York, the prediction here is, and also the very coast of the West Coast, is that in July, the disease will stop spreading. Now, if that happens, if they're right, then that's going to be a disaster, because I think it's very likely in America and also the UK that people will say, oh, turns out this disease is not a problem. It didn't really take off at all. The scientists were wrong. People will go back to
That's essentially what happened.
And we could see what happened in 1918.
Yep.
Flu virus of like the second go around when winter hits could be much worse than the start, right? So like there's these kind of like huge potential policy impacts depending on whether this is true or false. And so to think about it, yes.
I also just wanted to say that it would be very irresponsible to think, oh, summer's going to solve it, we don't need to act now. Just in that this is something growing exponentially and could do a huge amount of damage.
Yeah. So it could
I mean, already has done a huge amount of damage.
It could be a problem either way. If you assume that there will be seasonality and that summer will fix things, then it could lead you to be apathetic now. If you assume there's no seasonality and then there is, then you could end up kind of creating a larger level of expectation of destruction than actually happens and end up with your population being even more apathetic. So that being wrong in any direction would be a problem. So one of the ways we tend to deal with this with this kind of modeling is we try to think about priors. So priors are basically things where we, rather than just having a null hypothesis, we try and start with a guess as to like, well, what's more likely, right? So in this case, if memory serves correctly, I think we know that like flu viruses become inactive at 27 centigrade. We know that like the cold coronaviruses are seasonal. The 1918 flu pandemic was seasonal. In every country and city that's been studied so far, there's been quite a few studies like this. They've always found climate relationships so far. So maybe we'd say, well, prior belief is that this thing is probably seasonal. And so then we'd say, well, this particular paper adds some evidence to that. So like it shows like how incredibly complex it is to use a model in practice for, in this case, policy discussions, but also for like organizational decisions, because, you know, there's always complexities, there's always uncertainties. And so you actually have to think about the utility, you know, and your best guesses and try to combine everything together as best as you can. Okay, so with all that said, it's still nice to be able to get our models up and running, even if, you know, even just a predictive model is sometimes useful of its own, sometimes it's useful to prototype something, and sometimes it's just it's going to be part of some bigger picture. So rather than try to create some huge end-to-end model here, we thought we would just show you how to get your PyTorch Fast.ai model up and running in as raw a form as possible, so that from there you can kind of build on top of it as you like. So to do that, we are going to download and curate our own data set, and you're going to do the same thing. You're going to train your own model on that data set, and then you're going to get an application, and then you're going to host it. Okay? Now, there's lots of ways to curate an image data set. You might have some photos on your own computer. There might be stuff at work you can use. One of the easiest, though, is just to download stuff off the internet. There's lots of services for downloading stuff off the internet. We're going to be using Bing image search here because they're super easy to use. A lot of the other kind of easy to use things require breaking the terms of service of websites. So like, we're not going to show you how to do that, but there's lots of examples that do show you how to do that. So you can check them out as well if you want to. Bing image search is actually pretty great, at least at the moment. These things change a lot, so keep an eye on our website to see if we've changed our recommendation. The biggest problem with Bing image search is that the sign-up process is a nightmare, at least at the moment. Like one of the hardest parts of this book is just signing up to their damn API, which requires going through Azure. It's called Cognitive Services, Azure Cognitive Services. So we'll make sure that all that information is on the website for you to follow through just how to sign up. So we're going to start from the assumption that you've already signed up. But you can find it, just go Bing image search API. And at the moment, they give you 7 days with a pretty high quota for free. And then after that, you can keep using it as long as you like, but they kind of limit it to like 3 transactions per second or something, which is still plenty. You can still do thousands for free. So it's at the moment, it's pretty great, even for free.
Did you previously watch this video, Martin?
Maybe.
All right. So when would be a good kind of stopping point to start going? Do you want to watch this?
I mean, so what he does now is he shows the notebook in action, essentially, like the bear classification. We can watch it, and
We're
I think
classifying bears on this one?
Yeah, we're classifying bears. I think we should watch over it and then just like last time, just play around with it a bit and look for some different images.
Okay. Cool.
We probably don't really. I guess we should do that on Friday. That we actually sign up for
Azure
Bing image search stuff and get like some, like I'd suggest maybe we can both try it in the meantime until Friday. Try a little model and then build another one on Friday together, or we just do it together on Friday.
Yeah, that's fine. So Friday we'll be building something on Friday. Cool. All right. So let's finish this video.
Cool. What will happen is when you sign up for Bing image search or any of these kind of services, they'll give you an API key. So just replace the XXX here with the API key that they give you. Okay, so that's now going to be called key. In fact, let's do it over here. Okay, so you'll put in your key, and then there's a function we've created called search images Bing, which is just a super tiny little function. As you can see, it's just 2 lines of code. I was just trying to save a little bit of time. Which will take your API key and some search term and return a list of URLs that match that search term. As you can see, for using this particular service, you have to install a particular package. So we show you how to do that on the site as well. So once you've done so, you'll be able to run this, and that will return by default, I think, 150 URLs. Okay, so Fast.ai comes with a download URL function. So let's just download one of those images just to check and open it up. And so what I did was I searched for grizzly bear. And here I have a grizzly bear. So then what I did was I said, okay, let's try and create a model that can recognize grizzly bears versus black bears versus teddy bears. So that way I can find out, I could set up some video recognition system near our campsite when we're out camping that gives me bear warnings, but if it's a teddy bear coming, then it doesn't warn me and wake me up, because that would not be scary at all. So then I just go through each of those 3 bear types, create a directory with the name of grizzly or black or teddy bear, search Bing for that particular search term, along with bear, and download. And so download images is a Fast.ai function as well. So after that, I can call getImageFiles, which is a Fast.ai function that will just return recursively all of the image files inside this path. And you can see it's given me bears / black / and then lots of numbers. One of the things you have to be careful of is that a lot of the stuff you download will turn out to be like not images at all and will break. So you can call verify images to check that all of these file names are actual images. In this case, I didn't have any failed, so it's empty. But if you did have some, then you would call path.unlink. Path.unlink is part of the Python standard library, and it deletes a file. And map is something that will call this function for every element of this collection. This is part of a special Fast.ai class called L. It's basically it's kind of a mix between the Python standard library list class and a NumPy array class. And we'll be learning more about it later in this course. But it basically tries to make it super easy to do kind of more functional style programming in Python. So in this case, it's going to unlink everything that's in the failed list, which is probably what we want, because they're all the images that failed to verify. All right, so we've now got a path that contains a whole bunch of images, and they're classified according to black, grizzly, or teddy based on what folder they're in. And so we're going to create a model. And so to create a model, the first thing we need to do is to tell Fast.ai what kind of data we have and how it's structured. Now, in lesson 1 of the course, we did that by using what we call a factory method, which is we just said image DataLoaders dot from name, and it did it all for us. Those factory methods are fine for beginners, but now we're into lesson 2. We're not quite beginners anymore. So we're going to show you the super flexible way to use data in whatever format you like, and it's called the Datablock API. And so the Datablock API looks like this. Here's the Datablock API. You tell Fast.ai what your independent variable is and what your dependent variable is, so what your labels are and what your input data is. So in this case, our input data are images, and our labels are categories. So category is going to be either grizzly or black or teddy. So that's the first thing you tell it. That's the blocks parameter. And then you tell it, how do you get a list of all of the, in this case, file names? Right? And we just saw how to do that because we just called the function ourselves. The function is called getImageFiles. So we tell it what function to use to get that list of items. And then you tell it, how do you split the data into a validation set and a training set? And so we're going to use something called a random splitter, which just splits it randomly. And we're going to put 30% of it into the validation set. We're also going to set the random seed, which ensures that every time we run this, the validation set will be the same. And then you say, okay, how do you label the data? And this is the name of a function called parent label. And so that's going to look for each item at the name of the parent. So this particular one would become a black bear. And this is like the most common way for image data sets to be represented, is that they get put, the different images the files get put into folder according to their label. And then finally here we've got something called item transforms. We'll be learning a lot more about transforms in a moment. These are basically functions that get applied to each image. And so each image is going to be resized to a 128 by 128 square. So we're going to be learning more about Datablock API soon, but basically the process is going to be, it's going to call whatever is getItems, which is a list of image files. It's then going to call getX and getY. So in this case there's no getX, but there is a getY, so it's just parent label. And then it's going to call the create method for each of these two things. It's going to create an image and it's going to create a category. It's then going to call the item transforms, which is resize. And then the next thing it does is it puts it into something called a DataLoader. A DataLoader is something that grabs a few images at a time. I think by default it's 64, and puts them all into a single, it's called a batch. It just grabs 64 images and sticks them all together. And the reason it does that is it then puts them all onto the GPU at once, so it can pass them all to the model through the GPU in one go. And that's going to let the GPU go much faster. That's what we're learning about.
Can you
And then
pause?
finally, we don't use any here, we can have something called batch transforms, which we will talk about later.
Do you understand how it gets? So I understand the get image files function is set up so that it downloads these images using the Bing API. But I'm wondering, I don't really understand how it gets the categories, because they also said like there's usually, you can have two different getters, one for, I guess, the data and one for the categories, getX, getY, but we're only using one. So I'm wondering, and the search term was grizzly, right? So the data points that he's getting is going to be images of grizzly bears, but it must be a couple of bears if it wants to categorize, right? Yeah, then it needs to be images of 3 of different types of bears.
Yeah, so I'm not 100% sure. I think we'll be able to like understand it more in the
I can hear Johnny
yeah,
working.
Johnny's like working in the back right now. I think we may understand it better when we see the code. Anyway, for me, like if seeing the whole Jupyter notebook, maybe I don't know, maybe we're missing something.
Do you want to look into it now?
Sure.
Or okay.
Oops, reconnect. All right, I'm just gonna put myself back on mute.
Well, okay. Maybe, yeah, I'm not sure. It might be useful to read over this, but let's see what we can. Combining text and images, not as just examples, gathering data. Azure sign up, clean, okay. Search images. And this, yeah, so he's inputting grizzly bear as a search term. And we must be getting a bunch of images, 150 grizzly bear images, right? Yeah. Okay. And then, okay, where's that? Okay, so he's running the function 3 times and gets them all into different and saves 150 images of each of them. Okay.
Yeah, it's and then just storing it as is this like bear and then whatever.
Okay, so
grizzly, black, or teddy, appending it to the type of bear.
Search images big key. Wait, where does it put that? Search images. Make directory results. Searching it. Okay, so he's putting it probably in the file name, right? That's
yeah.
I don't know what
it seems like.
Right. Yeah. Okay. So then.
Yeah, then the results ends up being something like this.
Bears black. Okay, so it puts it in a subfolder and then just gives it a name. Okay, so we have the labels by their location essentially.
Yep.
Okay, and then can you scroll down some more? The question about like how does it get it out? Okay, failed. We can check that. And then okay, no, we don't need that. This maybe, yeah. DataLoader. Get wait, I can image block category block. Get images. So that's that takes the function to download the images, but then get item. Wait, can you stay at this init function down there? This one, DataLoaders. Sorry, the class definition. Okay, so in itself, get item, chain word, self I. Yeah, I don't really see how he extracts the labels from that. What's the categories block?
I can't really get a word in without the table start running in the background.
It's all right. It's not too loud though.
Okay.
I mean, I can hear it, but. Do you know what I'm saying? Like, I'm confused about category block. I kind of think I understand image block, but I don't really get it where this data comes. Like, how does it get into category block? Because data block seems to be a combination of the image block and the category block. Maybe I should just read what it says here, huh? For the data, our underlying items will be file paths. We have to tell Fast.ai how to get the list of those files. Okay. The get image files function takes the path and returns a list of all the images in that path recursively by default. Okay. often doesn't. So we already have a validation set defined. Sometimes this is done by placing the images for the training and validation sets into different folders. Sometimes it is done by providing a CSV file in which each file name is listed along with which data set it should be in. There are many ways that this can be done, and Fast provides a very general approach that allows you to use one of its predefined classes for this or to write your own. In this case, however, we simply want to split our training validation set randomly. However, we would like to have the same training validation split each time we run a notebook, so we fix the random seed. We just don't really know how to create random numbers at all, but simply create lists of numbers that look random. If you provide the same starting point for that list each time, called the seed, then you will get the exact same list each time. Okay, that doesn't make sense, but didn't really yet explain my confusion. Are you equally confused by what I'm confused by, or not?
I'm confused, but also just trying to multitask everything.
I see.
I honestly, like, with this stuff, I don't know. I feel like so for me, I just need to, like, I don't know, kind of watch him kind of do it, get a sort of understanding, and then getting back into the Jupyter notebooks, like we did in the previous stream. How we, running this one line at a time, I think we get a better idea, and we kind of, like, read through it as we're doing. Because right now he's like, where is he?
He's somewhere there.
He's like picking and choosing like blocks of code. And you're right, like in this case, it's the only, I see like get y is equal to parent label, but I don't even know what this is. Right? There's no context to parent label.
Get y equals parent label. Well, okay.
Yeah. Let's just watch the rest of the video.
Keep moving.
Keep it moving.
And then somewhere in the middle about here, conceptually, is the splitter, which is the thing that splits into the training set and the validation set. So this is a super flexible way to tell Fast.ai how to work with your data. And so at the end of that, it returns an object of type DataLoaders. That's why we always call these things DLs. Right? So DataLoaders has a validation and a training data loader. And a data loader, as I just mentioned, is something that grabs a batch of a few items at a time and puts it on the GPU for you. So this is basically the entire code of data loaders. So the details don't matter. I just wanted to point out that, like, a lot of these concepts in Fast.ai, when you actually look at what they are, they're incredibly simple little things. It's literally something that you just pass in a few data loaders to, and it stores them in an attribute, and gives you the first one back as .train, and the second one back as .valid. So we can create our data loaders by first of all creating a data block.
I was just wondering that he keeps switching back behind with these faces of, like, some, I don't know, advertisement. They just keep flashing for a second.
What?
Haven't you seen, like, there's these faces that keep switching to a different slide that has all these faces on it?
Yeah, they're incredibly simple little things. It's literally something that you just pass in a few data loaders to, and it stores them in an attribute, and gives you the first one back as .train, and the second one back as .valid.
This,
yes.
I mean, maybe he's just really concerned with healthy skin. I don't know.
But is he trying to, like, subconsciously imprint something on us?
It could
like,
be.
Take care of your skin.
I think so. I think you're right.
Train
you're onto
your
something.
Skin. Validate your skin.
All right.
So we can create our data loaders by first of all creating the data block, and then we call the data loaders, passing in our path to create DLs. And then you can call show batch on that. You can call show batch on pretty much anything in Fast.ai to see your data. And look, we've got some grizzlies, we've got a teddy, we've got a grizzly. So you get the idea, right? I'm going to look at these different, I'm going to look at data augmentation next week. So I'm going to skip over data augmentation, and let's just jump straight into training your model. So once we've got DLs, we can, just like in lesson 1, call CNN learner to create a ResNet. We're going to create a smaller ResNet this time, a ResNet 18. Again, asking for error rate. We can then call .find tune again. So you see it's all the same lines of code we've already seen. And you can see our error rate goes down from 9 to 1. So we've got 1% error. And after training for about 25 seconds. So you can see, we've only got 450 images. We've trained for well less than a minute. And we only have, let's look at the confusion matrix. So we can say, I want to create a classification interpretation class. I want to look at the confusion matrix. And the confusion matrix, as you can see, is something that says for things that are actually black bears, how many are predicted to be black bears versus grizzly bears versus teddy bears. So the diagonal are the ones that are all correct. And so it looks like we've got 2 errors. We've got one grizzly that was predicted to be black, one black that was predicted to be grizzly. Super useful method is plot top losses. And that'll actually show me what my errors actually look like. So this one here was predicted to be a grizzly bear, but the label was black bear. This one was the one that's predicted to be a black bear, and the label was grizzly bear. These ones here are not actually wrong. This is predicted to be black, and it's actually black. But the reason they appear in this is because these are the ones that the model was the least confident about. Okay, so we're going to look at image classifier cleaner next week. Let's focus on how we then get this into production. So to get it into production, we need to export the model. So what exporting the model does is it creates a new file, which by default is called export.pickle, which contains the architecture and all of the parameters of the model. So that is now something that you can copy over to a server somewhere and treat it as a predefined program, right? So then, the process of using your trained model on new data kind of in production is called inference. So here I've created an inference learner by loading that learner back again, right? And so obviously it doesn't make sense to do it right next to after I've saved it in a notebook, but I'm just showing you how it would work, right? So this is something that you would do on your server in inference. And remember that once you have trained a model, you can just treat it as a program. You can pass inputs to it. So this is now our program. This is our bear predictor. So I can now call predict on it, and I can pass it an image, and it will tell me, it is 99.999% sure that this is a grizzly. So I think what we're going to do here is we're going to wrap it up here. And next week we'll finish off by creating an actual GUI for our bear classifier. We will show how to run it for free on a service called Binder. And then I think we'll be ready to dive into some of the details of what's going on behind the scenes. Any questions or anything else before we wrap up, Rachel?
No.
Okay, great. All right, thanks everybody. So we hopefully, I think from here on we've covered most of the key kind of underlying foundational stuff from a machine learning point of view that we're going to need to cover. So we'll be ready to dive into lower level details of how deep learning works behind the scenes. And I think that'll be starting from next week. So see you then.
Bye.
Bye. Cool.
Okay.
All right.
That felt long somehow to me.
I think because we just did it with no breaks. Last time we took a handful. We did some breaks, yeah.
Mm-hmm. Yeah, I don't want to always make you stop. I'll probably stop more often if I had the power to.
I think stopping is fine. Also, maybe for Friday, I don't know. We're figuring out a whole office situation for the department. So hopefully next week we won't have to be dealing with all this, and you'll have more of my undivided attention.
Yeah, and I think also, because our idea with this course is also that we're actually mostly, most of the time that we're spending on it is actually going to be streamed, right? So I think breaking it up somehow in 2 sessions, where we do 1 session where we actually watch the video, so today, and we just think over it on this high level, and then we have the other session where we're actually working on the project, maybe makes sense, I think.
Yeah, I think that structure makes a lot of sense. Where
Mondays,
Mondays we go through the lesson, and then we'll go through the Jupyter notebook, and then on Fridays, we can build something from what we learned, something different than what's in the notebook. Right. It could be another notebook, or it could just be, it could not. I don't know. Whatever, doesn't matter.
Yeah, just apply the concepts that I talked about in that week.
Yep.
And I think I have it set up like that on the schedule anyways, but maybe switched around. I think Monday, maybe we have to adapt this a bit or whatever.
Whatever. Cool. So.
Okay.
That's.
I don't really feel like doing this right now.
Awesome. Me neither. Let's just start running
That's
this, yeah?
I like that more. Okay.
All right, so this should still.
Are you still hooked up to the GPU?
I had to reconnect, so maybe I should
Okay.
rerun this. I don't know.
Try.
Yeah.
What does it do if you run it? Yeah. You're gonna have to log
Alright,
in again.
seems like
or is
it's
it fine still.
seems like it's already downloaded though.
Cool.
All right.
I gotta do that again. Okay.
Okay. Cool.
And it's still running on the GPU. Can you just double check in the runtime, just so we don't?
Oops.
GPU, nice, good.
Yeah, you saw it. Okay.
Yeah.
All right. So, skipping all of this.
Yeah. So, do we have some sort of okay? We're just gonna run it with their.
Oh, we
Grizzly-
need to
no.
like do.
Yeah,
need
we have to sign up for that first.
Oh,
Oh, that sounds boring. Too.
sounds super
Wait.
boring.
I guess it's good to do it on the stream because it's probably kind of like messy. But I don't really feel like doing it today. So, do we have some sort of like data set we can just play with for today instead of searching for the images? Maybe there's like a small, a small image data set of something that we can download.
You want to look for a data set?
Yeah, not a big one. Like this was 150 grizzly, like 150 images, so like 450 images altogether.
I mean, it doesn't matter. Like, I don't care about the size. I just don't want to sign up for Azure right now.
That's what I mean. Yeah, so maybe just
Yeah.
download some data set. Just it's
All
already
right.
done.
Where
I don't know. Let's
Grizzly
see.
Bear.
Now look for something else. Let's do.
I mean, all the code in here is all set for grizzlies. So,
Okay.
also, yeah, we would have to. All right.
We could skip a lot of the code because a lot of the code is actually fetching it. We'd have to define a different data fetcher, I guess, but that could just be a
Grizzly
downloaded
bear
from wherever this is.
foraging areas, population estimates. Let's see. Where are they getting it from? Oh, they're just doing
go
a
for,
Bing
like,
search.
they're doing Bing search. Yeah. Just do like image categorization data set for deep learning or something like that. It doesn't have to be grizzly bears.
Yeah, whatever.
Products. I know, take away product, otherwise we're gonna go too much into that direction. There. There was a 50 free machine learning data sets.
All right.
Yeah, try that.
Oh, this is just telling you where to get them from. All right.
Yeah, that's cool. Let's just get one of those.
Oops. That's a lot of text.
ImageNet. Why not ImageNet?
I don't know. Should we just do beards?
A beard categorizer. I think that sounds fun. Okay, so you get like, what's that? A bunch of black bears. Cinnamon.
I don't know what's.
Beast of burden. Judgment. Animal such as a donkey.
Part of me feels like we would have already signed up for Azure. What is this?
Common
objects in context. Coco.
Object detection, segmentation, and captioning data set. Well, look at that. Images. 2014 train images. That looks like something you can download. Not train. What kind of images though?
It's also a lot of. This is
a lot of gigabytes. Yeah.
Yeah.
Yeah, we really don't need so many. We just need. There's something. I know that's annotations. That's not yeah. Image coil 100 datasets. Look, there's a get data. I don't think that's going to be that easy, especially since he mentioned that it's like a pain in the ass. It looks like a big 1.74 million images looks big.
Can we just copy some of this
that
stuff?
was okay. Check out the dog data set. Images 752 megabytes, 120 categories. That sounds okay. That's not too big, right?
I know, but what do we need this and the annotations?
Yeah, maybe. We definitely need the images. And yeah, I don't know what the annotations are going to be, but and you probably don't need to download it like that because we're going to have to download it in the notebook, right? Okay, so for more information about the dataset, please visit the website. Attribution. Thank you, vision.stanford.edu. Images of different breeds are in separate folders. Perfect. Annotations, bounding box annotations of images. We don't need that. File list. So really, yeah, I think maybe you can try to just download it in the notebook.
Yeah.
Like get the link that you were downloading from.
So key, we don't need that. We're not going to do that.
So you're gonna have to.
I don't want to do any of this right now.
You don't? I'd be up for trying it. I could take over.
Go for it.
If you want. Okay. Share. You gotta stop sharing. Okay, let's see. So I still got that one. I need to connect it to a different runtime. Change runtime type. Save. Getting connecting and run. Then we said that was Stanford Vision Dog Dataset. Datadog, no, this one. Images. Okay, so this is the download link. So I'm gonna get the link address. Yeah. Okay, let's do that first. Good. Okay. So we need the link to this, and let's see if we can do that. Did that run? Yeah. Okay. Clean. So image open. So somewhere in here, right? Let's start a new cell or get rid of this stuff.
Okay, what we're trying to do is download this. So I guess I'm gonna have to pip install requests. Already got it, good. Then I wanna say, can I just do that directly? Requests.get our URL. Oops. And then what does that? And then we're gonna have to untar it. I wonder where this downloads it to. I don't know. Download. Maybe we should do that with Bash. I really wonder where this saves stuff in if we download something there.
Yeah, I have no idea.
Did he just load it into memory or what? Response raw. Import requests, target path, requests at get, stream equals true. If response 200 with open binary. I don't actually want the tar file, I want to untar it. Or so when he gets them, he tried one of them, right? Because he's doing calls specifically.
Well, so like the like IMS results that.
He just gets URLs, right? He just gets URLs, so then he can download each item separately.
Yeah.
We have a tar file. I don't even know whether that works. Can I? Like, what's the file system that Colab uses? Downloading folders, datasets from Jupyter Notebook. Or running it from a computer, makes sense. Running it from a server, downloading one file at a time. There's a new extension. Just one folder. Zip, something like that. No, we don't want to zip it. Should we just try that? Is there like a file system? Okay, let me see. Let me see what happens when I say ls in here.
Okay, so it looks like it's the what's in your Google Drive, right? So if you open up that little,
so I can go into G Drive here, and then look what's in there. Or what? My drive looks like it. So wait, so I can. Let's see what the file path is for that. /content/G Drive. So maybe we can just download into.
Yeah. So, what is it? Content, G Drive, my drive, sample data. Oh no! Hold on. If you what was it when you just did ls? In there, there was G Drive and something else.
We're doing it. The other one before that.
Yeah.
So at the root, it seems we have
sample data.
G Drive and sample data.
Okay,
I don't know what's in there.
Yeah, what's in sample data?
Unscope, California housing test, MNIST train. That looks like some machine learning stuff, but it might be something I did a while ago. I don't know. It could be, but I guess we could use that directory. Doesn't really matter.
Yeah. You can make a new one too if you want, whatever.
Right, let's just make one, yeah, why not? And we call it dogs. And then, whoops. And then let's see whether that worked. There it is, nice. So if I cd into dogs, and let's get the path so that we know where to download.
Content dogs.
Okay,
Yeah.
/content/dogs. So now I guess we could be able to save this file, download it and save it. We can try the code that this person, we could also do wget, I guess, right? No need to go over Python.
Yeah. Give me 1 sec. I'll be right back.
Okay. Now we'll just play around with this in the meantime. See if I can get it to work. Wget. How do I do that exactly? Dash get download. Postface. Wget domain.com file.txt. And then I can put it, I guess, run it from and first the name. Is that first the name? Get docs. -l, and then I can give it where I put it to. 0. Now I still get the wget. Just try that. Wget. No, that's maybe where I want to put it. And I think I'm gonna go from here, content docs. Let's see what happens when I do this. Invalid syntax. Get. I need to put this into quotes. No. Maybe no need to put this. Move it. Syntax invalid syntax. HTTPS. Ah, stupid. Forgot the exclamation mark. /content/docs. Okay. Seems to be working. Let's see where it goes to, whether it goes into the right folder.
All right.
That's it.
I'm back.
Yeah, hi. So seems like the download is working. I'm not sure I'm actually putting it into /content/docs, but we can always move it. And it's going pretty quickly.
Nice.
Okay, so that's done. See where it is. Yeah, okay, so I just moved it in here. Let's move, I don't know. How do you untar? Is it untar? Or just into dogs? Is that how it works? No.
What are you doing? What are you looking up?
Do you know how to untar?
Oh,
I thought it's maybe untar. Open a tar file. Untar. Ungzip. Tar. Oh, okay. Not untar, but tar. Invalid option E. Try tar help. Tar. Extract the tar file. Okay. I just uncompress directly there. Extract and uncompress. Extract and uncompress.
I guess I want to do that. X-fifths. X-fifths. Let's just extract it right here. Not in gzip format. Child return status 1. Error is not recoverable. Exiting now. Okay, let's see. Without options. Hold option G requires an argument. Bruh.
Oh yeah, go back to the other the documentation for tar.
That's not very extract
extract
files
files
from an
from-
archive. Verb
Okay, so if you just did archive,
-x.
yeah,
Decompress the contents of the compress created by gzip. So because it's not, I don't need set. Specify an archive or a tarball file name -x. Let's try again. -x f because I want to specify the file name. It looks like something happened.
if you yeah,
It's probably in their images. There it is. Nice. Okay. So now I can move images to dogs. And then cd dogs. And there it is. Nice. Okay.
Cool.
So I think we always start like it looks like it always starts at the root. So not, or maybe I am in images now, actually. I'm not sure. Let's try.
I think you should be in dogs
If
right
I
now.
right, that's what I meant. I'm not sure that it, yeah, see, it always starts from outside for each new cell.
Okay.
So I'm gonna have to do cd dogs images to just take a look what's in there. All right, look at that.
Sweet. Ooh, that's kind of
And these are folders. I think these are probably folders. And then each of them has a couple of images in there.
yeah. This
Just checking.
Vizsla,
Yeah. Yeah, that's how it works.
this dog
Vizsla?
called Vizsla. Yeah, I've never heard of this breed before. And then
Wait, where? Where did
up,
you
up,
see that?
it was up more right there. The
Vizsla.
yeah.
Okay, let's look at a Vizsla.
I've never heard of this dog breed before, and the other day I was out to dinner with Regs,
You know it. Okay.
with Reg, and this guy was like,
Yeah.
"Oh my God, is he a Vizsla?" I was like, "I don't even know what that means." So I looked it up, and I'm like, "No, he's. I mean, he could be. I don't know. He's a mutt, but I don't think he is." But
Funny.
yeah, it's very interesting. Oh, there you go.
So do you think I can, I can open it probably image.open
Just go to
and then pass in this as a path.
yeah.
That should work. Let's try. So image would be, let me see, I'm going to put a path.
Or just type in
Would be-
change the destination to what you want the full path to be. Yeah.
No, and that was at content like that, right?
Yeah, and just put a slash after Vizsla before the N.
Thanks. Test, yeah, right.
There you go.
There it is.
There you
It
go.
does look like Regs. It does look like Regs.
A little bit, but like if you see the side profile, the nose is a little different.
Yeah, that looks
And
different.
the ears are much longer. Yeah, on the Vizsla.
Well, I guess we can build this classifier and figure out whether
Is-
Rex is a V-star?
Yeah, we could do that. Let's do that.
So one thing I'm confused about is that it doesn't seem to be cutting them into squares. Like here, it seems to be saying, let's make it 128
Well,
times
so
128.
you're also like, is image.open? Oh, no, I guess IM is, yeah.
Right? So, I mean, there's probably more we can learn about the image,
Is there a
like
dot?
maybe aspect. That could be interesting. Maybe that tells us one. Okay,
Oh,
that doesn't tell me
interesting.
anything.
Well, yeah, no, it's 1.5.
Was that, yeah, so, right. So, but it doesn't seem to be cutting them. I expected that it would, that's kind of what it looked like. It kind of looks like a 1.5.
Yeah, like a 2
Right?
by 3 or
Yeah.
something, whatever.
It's like, but so maybe it just takes it shows, it doesn't cut it actually. It just shows the it just cuts one side to 128,
Right,
and then
maybe
whatever is
the
the other one.
longest, yeah, maybe it just keeps like the longest
Yeah.
side to 128, and then it doesn't matter what
That
the
could be,
shorter
yeah.
one. Yeah.
Okay, cool, makes sense. All right, so we got these things
Oh,
already,
all right.
and
So
we
let's,
got them.
yeah, let's do let's
What's
try
the
to
name
figure
of our
out.
folders?
Let's try to
Oops, where did I go?
I guess we're building the project now,
Sorry.
sort of.
What?
I guess we're building some
Yeah.
sort of a project now. Let's do
Well,
let's do what kind of dog Regs is, and we'll do 3 types of dogs and see the percentage. Because we think we think he's a Chesapeake Bay Retriever, and I have a feeling he has like a little bit of pit bull in him as well. So we could see
well,
like,
we can just run it on all of those, right?
That's
we
what I'm
don't
saying,
have to
we-
have 3.
well, if you train it, oh, sure.
We just train a classification and we figure out what is most of those.
Yeah. And then, so I guess write like a little script now for bear types and just get like dog breeds and to trim out everything that like first part so that you could just get the breed.
Yeah.
So
Yeah.
it's
So we get the names. Did we get these names?
Yeah. So everything until
Sorry,
the
it was
first
lagging a bit.
slash.
Yeah.
It seems
yeah.
like.
Yeah, it seems pretty easy. So then we get just a list of those. Okay, let's do that. Oh, they're in the way. Huh.
We're gonna
Make
see
it
he's
so.
like part Chihuahua.
Why am I down here? B. Oh, there you go. Okay. So I like to use these shortcuts, by the way. I don't know if you know this. If you're on in insert, if you're not in insert mode, you can press A or B to make a new cell either above or below.
Okay.
Kind of useful. Yeah. So we want to get content dogs images in from pathlib path. And then we want to say there's probably inbuilt stuff that does that already. I assume in Fast.ai. I just don't know about it. And then I think this works in a way we can say path dogs images, or I mean that for see what I'm messing it up, not iterable. Then there's something dot, what can we do here? Path dogs image, content. Was it at the root like that? Content dogs images?
Yes.
Okay. POSIX is not iterable, so I have to call something on that dot, what is it, config? Iter? Just guessing. Okay. this is what I want. Iterate over. I need. Oh, doesn't help. Path.glob. Path for child in P iter. That's what the function is called. Iter. Okay, so here they are. And then we can say d.name.split at slash, which is only here, and get the second part of that. That should be our things. And we can say breeds equals d name split zip for d in path editor. Okay. Where are we? Okay. And this should path bears. What's he doing there? Breeds. Okay, so we got the name of the breeds in the list from the different directories. That's our bear types.
Nice.
That's our breeds.
Need some points on the board.
So now what is he doing here? Path. So he's making a path object. We can do that too. Into, that should be that one, if I understand it correctly, where he has then the directories with the different pairs. All right, we don't need to make those. We already have them. And we already have the images in there. Okay. Function. So now what's he doing here? Our folder has image files as we'd expect. Get image files. Path FNS. Get image files. So that's the function we define. Do you remember what's this about?
It seems like it's
So wait, let me
it's
just try that actually.
creating,
So
like, what is that? A path? Yeah, just. I think you could just run that. Hold on. No.
this? No, we don't have get image files. That's a function that he defines somewhere, I think. No?
It's not anywhere.
Oops.
I mean,
Okay, let me try.
Just try running it. Yeah. There you go.
Oh, you're right. Okay, so all right. So he defines this function somewhere.
Wait, hold on. But now we have content dogs, images. This like.
Yeah, that's perfect.
Oh. Okay.
That's it. That gives us all of the different.
Yeah. I was gonna say, if you want to like create something quickly, I guess it doesn't matter, but to clean it up a little bit, to change the directory to just have the breed name. But you could do it, you could do it to clean it once, or that we could just do it later to just disregard everything from the beginning. But I think cleaning it first would be nice.
Well, you don't want to have these numbers in there, is what you're saying, or what?
So on the images, it does. Yeah, exactly. So on the image, doesn't matter really. Just so that.
Yeah. Yeah, right. I mean, we could just rename the directories, is what you're saying.
Yeah.
Yeah. Okay.
And if you want to go just above and beyond, make them all lowercase to standardize them. So I don't know. I'm just giving suggestions at this point.
Okay. Yeah. I see what you're saying, and I think we could do that. I would not do it right now because the worst thing that happens is that in the output we get this thing. We still know what it's about.
Okay. Fine. I got you.
I do not watch my own content.
I got you.
Let's see whether anything is corrupt in there. Verify images. only then if we now classify Regs and it turns out that he's a N021020040 dash English Springer, then it's going to be hard to tell people about what breed he is.
Right.
Hey, what breed is this dog? Oh, it's an N021. Zero. Wow, perfect. Okay, so we don't need to do that. Sidebar getting help. What is that about? Verify images. Yes. Oh, that's just some info about Jupyter. I'm going to skip that for now. And sidebar. Oh, look, here they are again. Healthy skin. Reflect the data used to train them. And the world is full of biased data, which ends up reflected in, for example, Bing image search. So you were interested in creating an app that could help users figure out healthy skin. Young white woman touching her face detector. I like that description. Okay, good point. Biased data again, yeah. From data to data loaders. I guess we can, since this is a Stanford dog data set that's specifically designed for distinguishing dog breeds, I think that's exactly what we're using it for.
Yeah.
Well, we're just going to take over whatever bias Stanford put into their data set. From data to data loaders. Okay, data loaders is a thin class that just stores whatever data loader objects you pass to it and makes them available as trained and valid. Although it's a very simple class, it's very important for Fast.ai. Provide just 3, 4. Okay. Data loader. Bears. Dogs. Get items. So this, we can still use this function, right?
Yeah.
Yeah, okay, perfect. Split it. The parent label is still going to work the same way too, probably, right? Because they also had it in...
Yeah, it's just going to be messy.
Right.
Well, actually, so did you did you clean for the labels? Oh wait, get parent.
No, the label's just gonna have the numbers in there. I didn't do anything.
That's fine.
I made this list. I made this breeds list, but we're not using it because I didn't go and rename the folders.
Yeah. That's
based on it. Yeah. So it's just a little side task.
Cool. So
okay, let's look at each of these arguments in turn. First, we provided tuple, specify dependent variables, image block, category block. The independent variable is the thing we're using to make predictions from, and the dependent variable is our target. Independent, using to make predictions from. Image block, dependent one is our target. Okay, so independent variable are images, dependent variable are the categories, type of dog for each image. Whoops, excuse me. Where were we? There, okay. We will see many other types of block in the rest of this book. For this data loaders on a file path, we have to tell how to get the list of those files. Get image files function takes a path and returns a list of all the images in that path. We'll already have a validation set defined. We don't do that, we split it. Independent variable is X and the dependent variable is Y. Create the labels in our dataset, get Y parent label. Parent label is a function provided by Fast.ai that simply gets the name of the folder the file is in. Okay, there you go. Because we put each of our bear images into folders based on the type of bear, it's going to give us the labels that we need.
Cool.
And that's exactly how this dataset is structured.
Yeah, so you just have to run the cell before this.
I did already, actually.
You ran dogs?
Yeah, you see, when you got this number next to it, then it means it ran already.
Got it. So just, yeah.
So now I just got to say, I could have made this also easier and not rename, but let's stay descriptive with our variables. Okay, so this command is given as a data block, creating data loaders. We still need to tell Fast.ai the actual source of our data. In this case, the path where the images can be found. That's what we're doing here. The data loaders includes validation and training data loaders. Data loader is a class that provides batches of few items at a time to the GPU. We'll be learning a lot more in the next chapter. 64. Okay, let's look at it.
now we don't have to change anything anymore. We should see some dogs. There they are.
Okay.
Brittany Spaniel, Basenji. Do you know all this?
I know the Brittany.
Breeds?
Yeah, the Brittany I know, the Basenji I know, and then Mexican hairless I've also seen before. I've never heard of a Dandy Dinmont.
Dandy Dinmont. Okay. Crops to fit requested, losing some important details. Yes. Okay. Bears. Bear new. Oh, wait. So now we're going again. Wait, what do we want to do?
Dogs.
Alternative, you can ask Fast to pad the images with zeros, black. Seems like it's doing that by default, huh?
Yeah.
Or squish stretch them. We don't want to scratch them, right?
I don't think so.
Yeah. Let's look at it though. Why not?
I think it. Oh yeah, yeah. You can.
Or do you want to just stick with?
I think you could. It's just doing it.
No, let's play around with it.
Yeah,
we can always
play,
run it again. Yeah. Yeah, look now, it's got a black thing on top.
Yeah, and it's
so maybe that's
a
part
little
of
bit.
the squishes them around a bit, yeah.
Yeah.
Looks worse though, I have
Yeah.
the feeling. Or I'd imagine that it's.
So that's yeah, okay.
Yeah, I mean, with the one batch that we're looking at,
I think the first
more.
the first one looks the best so far.
Right, yeah, it doesn't seem like it's losing important data here. X number 20. Yeah, that looks, I mean, I'm just looking at a small part of it, I know, but that looks fine.
Yeah. All right.
Interesting that some of these images seem to be pretty small, huh? If it already gives them black bars.
Well, the black bars are just for the aspect ratio. It means it's not a square.
Yeah. And that seems to be the default, huh?
Yeah.
Okay.
All right. So let's
all of these approaches seem somewhat wasteful or problematic. If you squish or stretch the images, they end up as unrealistic shapes, leading to a model that learns that things look different how they actually are, which we would expect to result in lower accuracy. If we crop the images, then we remove some of the features that allow us to perform recognition. If we're trying to recognize breeds, or dog or cat, we might end up cropping out the key part of the body of the face necessary to distinguish. If we pad the images, then we have a lot of empty space, which is just wasted computation for our model and results in a low effective resolution for the part of the image we actually use. Instead, what we normally do in practice is to randomly select part of the image and crop just that part. On each epoch, which is one complete pass through all images, we randomly select a different part of the image. Interesting. This means that our model can learn to focus on and recognize different features in our images. It also reflects how images work in the real world. Different photos of the same thing may be framed in slightly different ways. In fact, an entirely untrained neural network knows nothing whatsoever about how images behave. It doesn't even recognize that when an object is rotated by 1 degree, it still is a picture of the same thing. So actually training the neural network with examples of images where the objects are in slightly different places and slightly different sizes helps you to understand the basic concept of what an object is and how it can be represented as an image.
Interesting.
Here's another example. Yeah. Here's another example where they resize with random resized crop. Blah, blah, blah. Interesting.
All right, so let's run that one.
Yeah, sure. I love that image. That's a very that was surprising. So is that picking a random one?
It seems like it. Oh no.
No, let's look at, but it's cutting it differently. Look, interesting.
Yeah.
Yeah, look, like it's taking always, it's the same image, but it keeps cutting it in a different ways.
Yeah.
Interesting. Data augmentation. Yeah, let's look at this more the next time, like because he also didn't go over it in the lesson.
Yeah.
I think he's gonna do it in the next one.
All right, so let's train the model. Let's see what we can
training the model. Let's see, and then try to classify regs. Does Jupyter have a? Oops.
I think you could just change the other one. Just change that one. Yeah.
I just need to change this really.
And
the
that's
rest is
it.
fine.
Everything is fine. Yeah.
I was just wondering whether we can edit a couple of things at the same time. Learn. All right.
We're on a GPU, right?
Yes, we are. ResNet 18, so it should be even faster.
Cool. I wonder what's going to happen with this confusion matrix. It's going to be so big. It's going to have all those like numbers, those like random numbers and stuff too.
You're right, yeah.
Yeah, this.
Oh yeah, that's like how many breeds?
I don't know.
Oh wow, it's a lot of breeds. I could check, but I can't run it right now while it's training.
So funny. Anyway.
We'll see. How many epochs are we doing? We haven't specified that really anywhere, right? Also not last time. Should clean up my tabs.
Now's a good time to clean up your tabs, go use the restroom, order yourself a sandwich.
Make sure that you're actually running on a GPU. Make it click that. Yes, we are. What's that? I don't need that. Hope I didn't terminate something wrong now. It looks okay.
Yeah.
So it's in the second time of running the progress bar, whatever exactly that means. I don't know, but I think
like
then we were getting, yeah, the second one was faster, and then we were getting the info, the loss. Yeah, there it is. And that's the second epoch. Maybe that's just it.
Oh wow, the loss is pretty high.
Valid trained loss. The last one was like 0.5 or something.
Yeah.
See whether the second epoch improves on that. Yeah, the confusion matrix is going to be huge. You got an image ready for me to try out?
I'm gonna take a fresh one.
Ooh, I can get it from Imgur.
Imgur, as you like to say.
Imgur. Imager, this is how I say. Imager.
Well, I think I actually do have a nice one.
Imagine how long that would have taken without the GPU.
Oh my goodness.
It's already taking kind of long. Also interesting that, so I wonder how many images we have. I guess we could figure that out too. Probably it says it here. That's easier. Number of categories. Oh, okay. 120 dog breeds and 20,580 images. That's what we're running this on.
Okay.
Yeah, and in the example with the bears, it was 450 images, right?
Yeah.
And
that took 28 seconds, so.
Yeah.
Just waiting. Where do you want me to send you this photo? Slack? Zoom?
Zoom. We got that open. That works. Or you can put it online somewhere and I can just download it into the notebook.
That's true. Trying to find a good one of his face.
Oh wait, actually maybe that's easier because otherwise I'm gonna have to figure out where to put it. And I guess if I upload it on my drive. This cloud storage is interesting to think. Like where does it go if I upload it to Google Drive? Now I know it goes into /contents/my drive.
If I give you, interesting, I don't know, can I give you an iCloud link?
Probably. Oh no, I might have to, if it's public, sure.
Let me see if it is.
Should I just go to Imager? You have like a picture of Regs on there, right?
It has like other text and stuff on it, but maybe.
Is there not like just a direct image link?
Hold on, I just got
Okay.
a link.
So it looks like it's gonna do 4 epochs, and we finished the first one, and now it's gonna finish the second one real soon. And then I guess we're halfway done. The loss went down. Yeah, so we're halfway done now. Okay, I see. That's the point of this upper progress bar.
That's nice.
It's really, yeah, it's really intuitively designed, it seems. Such pretty colors in the progress bars. African hunting dog has by far the most images. Chihuahua has the least. 15 train, 100 train. Not sure what that means. Oh, does the accuracy of... Oh, maybe I don't understand what that's about. That's a beagle. Affenpinscher. Cool, you can look at the images online for this one.
Nice.
Keep shifting around. You got the picture?
Yeah, I'm sending. Oops. Sending you a few photos.
And you're sending them as photos?
No. Links to photos.
Links, okay. I think I'm gonna have to exit the screen share to access them. Yeah, do that.
That's fine.
Oh yeah, cool. There they are.
So the second one, it kind of ignored that. Just whatever ends with that JPEG.
Right. Okay, so we got those. That's unfortunate. So one of those two.
see.
say double G or one
just
G?
1G.
Okay. Okay, so. Oh wait, I should do it. Sure, it's easier like that. I'm just gonna do wget again, like before.
Mm-hmm. Oh, did it? Oh, so it finished.
Oh yeah, we're finished. Nice. 120 breeds. We already know that. And then look, it got down to 0.6.
Nice.
Trained loss and validation 0.7. Cool. All right, so
All right, those
we
are
got
downloaded.
We got these downloaded. Now I need to move them. Let's just see, they should be in here, yeah. I don't need to move them actually, but let's rename them. Oh God. But I want to give him 2 G's, it seems. And okay, whatever.
Cool.
Okay, a little easier.
I want to see this matrix.
Okay, let's do that. That maybe takes a little. And we want to see that image. What was the? Image.open. Okay, that's easy. You're still working on it. Content. Look at me, keep doing that. Okay, so that should be 1. And then we can duplicate this, I guess. What's that? Mirror cell in tab. Copy cell. Paste them in this or in a different block. Oh wow, look at that. Oh my God, that's useless.
Oh man. This is like, remember when we did that, when we ran analysis on that like reviewer data set. And I forgot which one it was, but it was like so useless. This is exactly what this reminds me of. But
yeah, we just have to make it bigger.
Yeah,
but it's still big.
That slash down the middle of like clean space is very interesting though.
True, yeah. I wonder what that means.
All right, let's
But yeah, it's gonna be 120 times 120. That's
and it's such
big.
a tiny space, yeah.
Yeah.
All right.
Okay, so we got. All right, I should save them to.
Oh wait, the clean one in the middle.
Yeah. Do you think it's just different colors, and then that's a good thing? Because in the middle, that should be
all the valid numbers.
Correct. Yeah, exactly.
But because there's nothing in the middle, maybe nothing is correct.
Hope not.
All right, let's try this out.
Okay, so we can plot our top losses, sure. Oh yeah, I see. Now this is gonna be a bit harder, huh? Number of rows. I have a solution though.
Look at you.
Nice, huh? Hacking it. Then it didn't.
So was it prediction?
I think. Good
So
question.
prediction, actual, loss. Oh, okay. So hold on, go do one of them. So
Prediction, actual loss. Okay,
so
so
the
prediction, then
prediction.
didn't.
Okay, so the second one, it says prediction was a Saint Bernard, which I
Mm-hmm.
would have thought also, but apparently it's a Tibetan Mastiff.
Mm-hmm.
And then the loss was 11, and then it thought it was
I think this is probability. Yeah, it was it was pretty sure that
pretty
it's
sure. Yeah,
and look at that one. That was totally sure that it's a then didn't.
I would have
Like,
guessed that too, though. That's obvious.
that's isn't that the breed that you said you didn't know about?
Yeah. All right.
Okay, yeah. It's pretty certain about some, like it, right? Like it's pretty certain about some of them that are just wrongly
I'm actually,
predicted.
yeah, like honestly, the Saint Bernard, I'm like impressed with, and then also that last one where it says it's a flat-coated retriever, but it's actually a Newfoundland. Like that's, I think it is a flat-coated retriever.
Well, you're just as easily fooled as this Resnut 18.
Clearly. All right.
Okay, so the intuitive approach, well, we're not very experts, but sure, should probably change it.
Okay, so
the
now
intuitive
it's
approach
like
to
cleaning this stuff to keep or
do it before you train a model. But as we've seen in this case, a model can actually help you find data issues more quickly and easily. So we normally prefer to train a quick and simple model first, then use it to help us with data cleaning. Fast.ai includes a handy GUI for data cleaning called Image Classifier Cleaner. And view the highest loss images in order along with menus to allow images to be selected for removal or relabeling. Wow, interesting. Do you want to try that?
Yeah, go for it. I have a feeling it's going to get messy because we have so many different categories.
Yeah.
As this is working,
train.
let's like scroll down a little bit more. What's next?
Okay. I think so. We're gonna go over all this again in the next lesson also, right? Like he said, he's gonna do data cleaning in the next lesson.
Yeah.
So that's cool. We can just play around and then whatever. Well, so we want to classify really, like this is other stuff. We really want to classify the picture of Regs and see what, right? Because we already trained the model. We got it. So, our model is interp. Is it interp? Learn. Was it learn.predict? Is that how we did it last time?
Let's look at lesson 1.
Yeah. Wait, was it? No, I went somewhere else.
No, it's Colab.
Yeah.
No. Yeah, notebook servers, or yeah, and then
I think that works. But and then chapter 1. Are you done?
Learn.predict.
Learn.predict?
That's, yeah.
Nice. Okay, let's try. And then I can pass it in an image. Let's see. Let's try this. Oh no, I didn't want to run you. Did I mess something up? Why does it not know interp anymore? Oh no, your session crashed after using all available RAM. That's probably because I opened up this other one.
Or because we just have a massive set for no reason.
Confusion matrix.
Oh, you use the Jupyter Notebook RAM.
It looks fine here though, right?
Yeah.
Wait, does it mean we have to train again?
No, I think you could just run that same block. Which block failed?
Don't think so. Like.
Oh yeah, I guess just get rid of
Yeah.
the stuff that you don't really need. Yeah.
It's all done. It's all gone.
All right. Let's retrain this thing, and then don't run the interpretation. Wait,
Yeah.
so everything is gone. So we have
Everything
to
is
go all
gone,
the way
yeah.
from the beginning. All right.
Correct, but we can do it a little quicker. And we don't need. This is what we need. Everything up to here. So
Well,
we
maybe
can
not
say-
everything. Maybe not like the displaying all that stuff, but
Right. Okay, let me just see. We're still on a GPU. And then what can we cut out? We don't really need that.
nope. No, we just need the first one that says dogs.
Not that it takes long. Like, I mean, these things don't really take that long. Anyways.
Or no, we wanted that last one.
Yeah.
The last one with the random images we wanted.
Really, the two things that takes a while, I think, is this import and then the actually making the model. Okay, I don't need this anymore. Oh, this is done?
Yeah.
Huh. So I didn't have to download stuff again. We got all the images. We don't need to download any of that anymore. We got the images. Don't need to just double check.
Okay.
Working. We don't need that stuff. We need the path.
Need that.
So that we don't need that. It's just a test. Don't need that. We don't need that. Okay, here's some. This is what we need. We can get dogs data block.
Okay.
And then the data loader from that.
Oh, do we have to run that one before the resize one? Item TFMS resize.
That's not a thing.
Okay, yeah. Okay. So
I think that runs later.
We don't really need that one either.
Okay, we got the images. We don't need to do these ones.
Let's do that one.
That one?
Yeah.
But that's just a example. I don't think it does anything.
Doesn't it?
No, I think that's just an example.
You sure? Because this is now loading it in like the different random resized crop. Or is this?
Well, it's doing, so that's doing something different than the one before. Here we did the data loader, and then here we did a different data loader.
Yeah.
Okay. So this is the one we actually needed to run. I see.
Oh wait, so it's doing. Oh no, I guess we didn't because we're doing it right.
You know,
here.
like this. Yeah, these two things did the same thing. Yeah. Okay.
So yeah, bears equals dog new. That's really all we have to do. We didn't have to run the one above, so that's fine. So we'll just run that.
Items. Yeah. Okay, and now this is going to take a bit again. Yeah, probably we shouldn't have tried to do this relabeling function because it has a limited amount of RAM.
Yeah.
And if it loads all of that stuff into memory, then it crashes. Good to know. Okay, we don't need that anymore. This leftover cells. We're not going to run this one. We got these two. Okay, so plot top losses. Okay, so here we want to classify Regs next. And you said that was learner is going to be our program, and then predict.
I guess just the destination, right? Or regs.
I'm not sure if it should be an image. I wonder what we're passing. What were we passing in the other one?
I'm checking right now.
Okay.
I think we just use a different Google account because I don't have it. Yeah.
But
It's
just
alright.
check the
Yeah, I'm
official
checking.
one. Do you want to share screen?
Oops. Oh, I'm like, why is this not recognizing anything? Because I'm in incognito.
I stopped the share if you want to share.
Yeah, hold on. Fast.
Because here it's just training, nothing interesting going on. A lot of interesting things going on, just I don't see what it is.
Oops.
First epoch is done.
Cool.
Oh no, not actually, just the first part of the first epoch. So I guess it's validating now, maybe.
Oh wait, what did we? Oh wait, no, I don't think that this is. Where was?
Yeah, it's chapter 1 intro. If you go on chapter 1 intro, that's the one, yeah. What we're looking for? I forgot. What we're putting in. Just search for predict. So that was a string, but that's, yeah.
Yeah, this is just for the IMDb movie stuff. So where was the cats and dogs one?
Wait, are you sure? I think this is just an example. Like he talks about the IMDb one too. But it still also talks about cats and dogs before. Because maybe we're not predicting, maybe we're classifying.
No, it was this one.
Right?
It was
Oh, you're right. Okay, it was the Jupyter Notebooks one. Okay.
Or maybe not.
No, it wasn't.
No.
Yeah. No, that's really just about Jupyter Notebooks.
Hold on. Where was it? I thought it was on.
Fast.ai, what are you looking for?
The one that doesn't have all this copy in it.
It's just clean, yeah. If you go to github.com fast.ai, fast lab, I think, or something.
Oh, that's what it was, yeah.
Fast course, something like that. Fast book, that's what it's called. And then clean, yeah. So this is inconsistently named, what? One is called intro when it's the notebook one.
I don't know. But this also doesn't have.
I think it does. This is just saying it's not only for image classification, but does it further up? I think it should show stuff about the cat even further up.
Here.
Look, probability, it's a cat. There we are. Learn.predict image. So image, yeah. It's an image object that it's passing.
Okay.
Pill image.
Interesting. I wonder if what we did last week now is just gone forever.
Oh yeah, I think it is.
Here, I'm gonna stop sharing my screen.
Okay. Yeah, I think it is. I don't think we saved it anywhere.
That's unfortunate. That was kind of nice.
Well, luckily we got a recording of it. We're 50% through here with the second run. I wonder, so I can't run anything in there. Do you want to keep sharing and look at, we could look into, like some of the docs. I guess I can just look into the docs like that and see how we can make the confusion matrix look differently.
Regs, after we figure out what kind of dog you are, we'll go to the park.
Hi, look, you can pass it a figure size argument.
7 by 7.
So
wait, so what was it? What was it before? Was it still like 3 by 3?
I don't know. Yeah, it doesn't have any. It has some default.
Yeah.
We didn't pass it anything. I guess we could pass it something like, I don't know, 120 times 120.
Yeah.
Or 60 times 60 and have it like half a whatever this is.
Yeah.
No, wait, that's 7, so 3.5. One of them would be half of them would be 3.5. Whatever unit that is. Anyways, let's first classify and then we can maybe try it.
Yeah.
Fixed size 7 tuple fixed size equals.
Yeah, I remember the last 50% was very quick compared to the first.
Was it?
Yeah, it was much faster. But maybe not.
I don't remember that. But
maybe it seemed like it was faster.
well, because we were having fun.
Were we?
Well, we can look at some cute dogs in the meantime. What
That's
about
true.
Arpenzella?
Should I take Regs into the camera, then we can kind of...
Wait, no. Can you say what was your idea? What do you think he is?
He's I think he's a Chesapeake Bay Retriever.
Chesapeake.
Chesapeake. Yep. There you go.
Bay Retriever. This.
He has this like a lot of these Chesapeake Bay Retrievers. They have like a white patch on their chest.
I haven't seen a single one of them.
But he has smaller ears and a shorter nose, which makes me think it's also a little bit of a like a pit bull terrier.
None of these has a white patch on the chest, Nick.
This is true. Very true. Oh, that one does.
Which one?
Left. Up. One. That one.
This one?
Looks like it
yeah.
does. Maybe it's a glare.
It's a glare. Shiny hair glare. This one has something white.
Yeah.
It looks weird.
It's very like fat arms. Very fluffy.
And what's another suggestion? Chihuahua? Is he part Chihuahua?
No, I don't think so. I don't think so.
Great image. Oh, that's why it's jumping. No, but did you say something else? Like another?
I think also pit bull terrier.
Mm-hmm. They don't have?
A pit bull would be, I think, 2 words. But I'm not.
Pit.
Terrier.
They have so the American Staffordshire Terrier.
There's a lot of terriers, but no
Yeah.
pit bull.
So that one, Staffordshire Bull Terrier.
Staffordshire Bull Terrier. We're done by
That's
the way.
right. You could see it right there. 155 images. So that's one type.
Uh-huh.
But I think he's got.
Also looks different, huh?
Yeah, I think he's got. So it's like some angles, he looks like this, or the.
Like this.
No, he doesn't look that cute. But all right, so look, we're done training.
Yeah. Done training. We're
Skip
back to
that.
0.6.
Skip that for now.
Skipping that, we get the images, and now we can pass the image to Regs 1. Or let's do Regs 2, that won't exhibit. To the predictor. Name learner is not defined. What? Learn. Okay. Regs 2 is not defined. Okay, I gotta run this. Shoop. And shoop. No. Okay, expected an input of type in pathlib, but got class PIL image. So it's
where was that?
It's expecting an image path, it seems. So I can just wait. I can do path.
Oh yeah.
Maybe. Okay.
Labrador Retriever. Okay.
Labrador Retriever.
Can you do Regs 1?
Yeah. Huh. Here's yours.
Yeah.
Here's a suggestion.
Scroll up to see. Let me see that photo. Okay. Let me see if there's another good photo of him.
Labrador Retriever, and then what's the tensor? Get a tensor. 57. I don't know what that means. Do you have any idea what that means?
Which one?
Like we're not really getting any, like what's the, how secure is it? Like,
yeah, I don't know.
How did we get that before? No, we didn't. Yeah. It must. I mean, I'm sure it's somewhere in there. I wonder what this object is if I assign it prediction.
I'm gonna send you another. This is kind of a silly photo. Regs, get out of there.
Okay, and then prediction. What can I do in the index? Count and index. See what they are. It's a function. Context one argument. Okay, that doesn't help. Doc prediction. Does that work? No. Dot count. Has no attribute name. Non-type? Shouldn't that be a something? It's a tuple.
All right, I just sent you 4 other photos from Imager of Regs.
Okay. Okay, so that's just what it is. We get the whole thing up. Okay. I'm gonna fetch them. Okay, I deleted all that code.
Oh, nice. I didn't know it supported multiple cursors in Jupyter notebooks.
Yes, sir. It does. If I do wget, do you know, can I like assign it a new name right away?
I don't know.
Looks like not. At least not like that.
Yeah.
Maybe with -o or something like that. Okay, I'm just guessing. Let's not do that. Oh, wait. Are you generally not happy about me? Line 6 input F. Am I doing something wrong here? Do you see what's going on? This 0 maybe?
No, it's on that last one.
Yeah, maybe. I mean, that's where it's complaining.
That's where it's complaining, yeah. Oh, maybe it is
necessarily mean it is.
No.
It is actually
It
at the
is,
last
yeah.
one.
All right, whatever.
I wonder why. Let's try again. Syntax error. HTTPS. What's the syntax error? That's puzzling. Is there like some weird character in there somewhere?
I don't know.
Strange, huh?
Just can you just get rid of the double slashes and then put new ones?
Uh-huh. They look the same. That's really interesting. I wonder what's... Huh.
So weird.
There was some weird character in there that looked the same.
Anyway, whatever.
I wonder what it was.
Yeah.
Huh. Okay. Oops. So if I was better at Bash, I could write a little loop to do that, huh?
Yeah.
But we don't really need to do that. I guess we don't really need to do that.
No, you could just copy. Yeah.
Yeah. Let's keep.
You could also just assign it there. You could assign it up there if you want. Regs 3, Regs 4.
Yeah, but we need the file paths anyway. Like we were passing it in with file paths. See? Okay, so
Right. No, I was saying assign Regs 3 the file path, and then just reference that.
Right.
Just so that you're not scrolling around.
I am planning not to scroll anymore here. Code. Okay. All right, so we have, I want to do this same code to whatever that is. No, we don't actually need to do that.
No, you could just do learn.predict, right?
Yeah. Still, I guess maybe it's interesting to see them, right?
Sure.
Let's see what happens if I pass only one value in. Still works. Okay, so this is the one that we're going to predict next.
All right.
Let's give it the prediction code. Learn.predict and then that path. Learn.predict. Okay. The plot thickens. Oh no, actually it clears up. We have another indicator for the same one. Then we do this one. And learn that predict. Oh, okay.
All right.
One more. How do I do that best? This is
Being lazy.
I should have just written a function. But whatever. Boom. And then that one's scary.
Let's see. I really,
American Staffordshire.
yeah.
Was that one that you're
Yeah.
also thinking of?
Yeah.
And I think we got one more. Happy with my copy pasting capabilities? Oh, hello. Is that like looks like a CV picture.
That is his CV picture. That was like when he was 5 months old. A Labrador Retriever. I'm not.
So-
Yeah, this one I feel like because it's black and white. But I don't know.
So we got your results are American Staffordshire, Labrador twice, so 2 Labrador, 1 American Staffordshire, and 3 Chesapeake Bay Retriever.
That's kind of what we thought he was too. Like, we think he's mostly Chesapeake Bay Retriever, maybe mixed with a lab, but then in like some photos he looks like a pit bull. So
Interesting.
yeah.
I mean that one, yeah.
That one's kind of silly, yeah. There's actually, so I haven't posted this one on Imager, but I can really quickly and send you the
Want to do one more?
yeah, let's do one more. I gotta post these photos.
Okay, while you do this, I guess I can write a little function here. So what do we do here? We want to see it first. And then second I print it. I wonder if it's not the only thing on the line. We will see. Prediction. Now I can just I guess it's image name.
actually just need to let's print this.
Oops.
Turn the whole prediction and print prediction. That I know. Make it first item and dash get first item. So that
All
Nick
right,
is
I just
happy.
send you 4 more photos.
Okay, I wrote a function to make you happy.
Nice.
It was a function to make you unhappy, but now I changed it, so now it's gonna make you happy.
Ah, thank you. Very sweet.
It wasn't on purpose a function to make you unhappy. Okay, let me get that. So you sent me what? You sent me 4 more?
Yeah.
Okay.
All right, let's do these 4 more. Let's see what breed he has, and then I gotta take him out because he's getting angry at me. Regs, this is for you. I promise.
Doing it for you. I wonder whether we're gonna get a weird. Look at that. XT, this one this time.
You want another bone?
I'm also not gonna know which ones we already looked at and which ones not, I guess.
Oh.
Ugh, this is so weird. I wonder what happens there. So what, I have to retype them or what?
What are you doing?
I'm just trying to get, sorry, I'm not sharing, huh?
No.
We're running into the same, wait, sorry, just a second, I'm gonna copy these again and then start sharing. So I keep running into the same issues again.
The weird like
yeah, the
character.
Weird, it's not.
Can you not just open them in your browser and then just copy that so that you're not typing it out?
Yeah, that works. On a Microsoft Word, what am I doing? TXT to raw, no, raw to TXT. I'm just wondering whether it has some sort of, you know, some weird character in there that I can't get rid of. I don't want a file. It'd be like that.
Yeah, just open up the 4 different ones in your browser.
That's what I get, you know?
I mean, go back into the chat.
No, yeah, I can
Open.
click them. I can't actually click them. I can click them. Okay. Let me share. And I can see. Oh dear. Okay, I got it. I'm back. Here's a couple of pictures. Yes, this is an easier way to do it. You are absolutely right. Number 1.
Did you want to find that? I guess not. To rename the files, or do you not care anymore?
Get give name to file while downloading. So that we also learn something. Wget original name.
What is that?
-O. Okay, so it's just a big O. I was I tried with a small O.
All right, you're close.
Okay, close. So this is gonna be Regs 3.jpg. Right. What's this one? Then
I'm telling you. Next 4. Five. And next 6. Okay, and now our RAM is still okay.
Yep.
Now we can say regs 3.
Oh wow!
Yeah,
I didn't
I
even
was
read I
worried
didn't
about
even
that.
read the function. Nice, man.
Let me see if I can, like, now it's a bit more useful, but we also want to see it. So let's try like this. There it is. Look at that. Beautiful, huh?
Handsome.
So Rex 3, she's a picky again. Laboratory again. This again.
All right. So Regs, you are a Chesapeake Bay Retriever. There's no doubt about it.
Very little doubt.
Very little
but
doubt.
not.
Come here. Come here. Let's. Ugh. I have all these like cables and stuff. Here.
Fun.
There he is.
Wait, are you showing him? I don't see him.
Oh yeah.
But the stream sees him.
The
That's
stream,
okay.
the world sees him.
Yeah, that's good.
All right, cool. So this was fun. We'll this Friday we'll build a cooler project with this.
Yeah, we can
did a
brainstorm
lot
a
of
little
work.
in the meantime.
Yeah. This will be fun.
Have some ideas, but this was fun too. Cool.
Yeah. All right. See everybody on Friday.
All right. Goodbye.
Bye.